Okay, so I announce that this is one of talks on topics in quantum field theory and string theory. I'm very happy and honored to be here, to appointed for the Louis Michel Chair. As a graduate student, I of course knew the name, and one of the themes on which he researched was phase structures of various theories. So this will be part of my talks. I'm also very happy to have this chair together with my colleague from my neighbor from a northern country, from Lebanon, Ali Chamsadin. Okay, now my general talk in this first two lectures are going to be about very esoteric things. So I would like to start by pointing out a letter which Klein, after he had been appointed as a professor in Stockholm, got from his friend, very good friend, Wolfgang Pauli. And this is part of what it says. Now, in case you can't read, it says, so this is to congratulate him. And he says, I'm not of the opinion that finding new laws of nature and indicating new directions of research is one of your great strengths, although you have always developed a certain ambition in that direction. I find much more beautiful those of your papers which deal with applications of known theories, such as, for example, and the paper with Nishina about the new scattering formula, etc., etc. Okay, so isn't it good to have such nice friends who tell you exactly what they think about you, that you should not leave any of your limitations, you should stay within your limitations and do applications. Now, I think I should mention that I found this in a biography, a short biography which mentions Pauli and Klein, and one should mention that Pauli did work on Kaluza-Klein series. So probably he just thought that Klein maybe got them by accident, and really it's he who should work on them. But maybe that's worthwhile mentioning. Okay, now for the last few years, Nature is sending us also a similar letter. And what appears here are various bounds, I'm afraid, on what could be possible masses of all kinds of particles which fantasy of theorists thought that they should be there. And we find that if they are there, they are heavier than what one expected. Now, right now there is some local, or maybe it will be global, excitement about one particle at CERN, which in a few months we will know if it's there or not. In any case, it doesn't immediately fit into any of the fantasies anyhow. So this is the letter we got from Nature. And so supersymmetry, strings, extra dimensions. Okay, now how are the scientists reacting? So we can say that we are just not listening, even though Nature is trying to tell us. Or we can say, like for many years, we just ignore and we have our own convictions on how things should be, and we hope that eventually our convictions will be listened to, and we will continue to work on those problems independent if we get this or not. And that's, of course, a risky situation, but let's say Thibault, which just was very honored to get a prize, I think expected for decades something which Einstein in the beginning refused at all to accept. And nevertheless, other people ignored both what Einstein thought about black holes and what he thought about radiation. And then both of them together somehow did give something. So the lectures maybe should be taken in that point of view, or maybe not. I will continue. And the first set of works I'm going to describe, the first topics, I'm going to describe issues related to geometry and space-time singularities, and trying to understand them. Work is done mainly with José Barbón. So this is, and I will discuss a long series of works on this subject and some things that we learned. And I will talk a lot about things that we don't really understand, because I didn't want just to present here closed works. I think them you can just find in the literature, but more, and this is a theme which will appear, more works which have still open ends in them, which need to be filled. And this is, they are all of them, no matter when they were done, work in progress. So the basic questions that I will try to answer here is, what does geometry capture when one studies quantum gravity? The diagnostic tools on which I will spend some time can be very long time correlations. They can be very small. And this goes under names like quantum noise and complexity. And I will describe, I will define in detail as we go on. And these issues I'm going to mainly discuss in a holographic setup. And the key thing of a holographic setup says that when you are in the conditions of ADS CFT, the theory is really defined by the CFT. And in the CFT, you can get the final non-perturbative results. The way how to attribute a geometrical description to them, when is it possible, to what extent is possible, is already an approximation. And the definition actually comes from the quantum field theory. This is more or less the attitude. Now, it would be nice if one could calculate in this duality on both sides independently. But it's not obvious. Definitely, we don't have the tools to do non-perturbative calculations on the string theory side, while in the quantum field theory, we do have much more knowledge, many more developed techniques. So really the point of view is the data, the information, to the extent that it exists, is secure on the CFT side. And it's less secure when you talk about the geometry and the bulk physics. So if I would say there is some relationship here, I would say the responsible adult in this relationship is a quantum field theory, because there the things are really, in many cases, clear-cut. While when one goes to the other side, we will see there are approximations, which is exactly the question, to what extent does geometry capture, or when I geometry, I mean semi-classical geometry, solutions of equations of motion, to what extent do they capture what is going on? And this will be related to issues like black hole information and also to the structure of space-like singularities. So the bottom line of a large part of the talk is going to be that geometry, and this will be shown by concrete calculations, geometry is very good in giving averages, even averages of very non-perturbative small quantities. However, there will be things which it misses, and we will show what it misses and what it captures. And this will be related both to the black hole information, so-called black hole information paradox, and to the claim that the Einstein-Rosen equals EPR, on which I will say a few words. I won't go in great detail, but I will show the details of the agreement, where the agreement is discussed. Okay, so I'm not going to review ADS-CFT. I'm going to assume that you already heard something about it. This condensed slide captures the basic claim. The claim is that n equal 4 super Yang-Mills theory, which has an SUN gauge group and is in 4 dimensions, describes the theory of a string moving on a background, I would say, which includes ADS5 cross S5 and a black hole at the very least in ADS5 cross S5, And there are specific ways to relate the parameters. I've written them here. Anyhow, in the case when I'm going to use them, I will bring them up again. Okay, now one of the most striking things, and now I'm discussing phase structure of the theory, is the very, let's say, surprising spectrum that n equal 4 supersymmetry is supposed to give us. So the result I'm showing you here is a result of an imaginary graduate student which appeared, let's say, 25 years ago in the office of his PhD advisor and told him, I have just succeeded to diagonalize the full spectrum of n equal 4 Young-Mills, n equal 4 SUN Young-Mills gauge theory in 4 dimensions. And I have I've calculated the density of states, and I find the following band structure of the theory. And the band structure of the theory contains a piece where the entropy goes like a power of the energy which is near to 1 but smaller than 1, 9/10. Then it has a part which goes like the energy, then has the part which goes like the energy to the 8/7, and from a certain point onward, it behaves like the entropy goes like the energy to the power 3/4. Now the region this graduate student is unknown to us is because his advisor kicked him out of his office and told him there's no way this can happen. And everything you write here is counter to how we usually think of field theories. For example, let's consider now Kaluza-Klein theories. When you have Kaluza-Klein theories, are supposed to be extra dimensions. But we don't see those extra dimensions. We live in our 4-dimensional world. So when are we promised to see the extra dimensions? When the energies will be large enough to excite these extra small dimensions, and we are going to see the particle, not just the zero modes, but the particle excitations there. And that is when we should begin to see the 10-dimensional, if it was a supersymmetric theory, aspects of string theory. Okay, but if that is the case, then the higher the energy, when you have these compact dimensions, the larger the dimension looks like. The lower the energy, like we are at low energy, the smaller the dimension looks like. Now we are going to see that this behavior is totally the opposite. This behavior at low energy indicates a 10-dimensional system. At high energy, it reduces the dimension, and there, that's not why the graduate student was kicked out. There it made sense, it's a 4-dimensional theory. So I'm going to show to you how these different things come, and they are going to play a role in our checking of what role geometry can play. So first the claim. The claim is that this part here signifies a 10-dimensional theory. This is characteristic of high energy excitations of a 10-dimensional field theory. This is characteristic of a free string theory. This is the Hagedorn spectrum, I'll remind you. Then comes a period which is characteristic of a 10-dimensional Schwarzschild black hole, a Schwarzschild black hole in flat space. And then comes indeed the 4-dimensional theory. So let's go to these various components. Okay, here is just what I said. That in general, if I have a field theory, and I will demonstrate to you, the entropy at high energies, the equal means that it goes in high energies like the energy to a power which is smaller than 1, and it goes like the dimension of space-time minus 1 over the dimension of space-time. For free strings, one expects that the entropy goes like the energy. For black holes in flat space, this is in general number of dimensions. You expect to have a power of the energy which is larger than 1. And in general, I will show again, remind you how you get that. But of course, a power larger than 1 creates heavy suspicion. because you have a negative specific heat for this system, so it's really unstable. You can't make thermodynamics in such a system, while black holes are supposed to be related to thermodynamics. And there are many other issues which come about once you have such a high density of states. So let's take first the radiation or a field theory. So
we are in a box here.
we are in a box. Always, I always put, I'm doing thermodynamics in a box, always. And for the black hole, we need the box anyhow. And for other systems, the box is for convenience, for putting an infrared cutoff. And so I can define the system, how it behaves. So in all theories which are conformal or asymptotically free, or I would characterize them in all theories which have a finite number of thresholds. That means that as you go to higher and higher energies, you do not produce at rest lots of new particles, but that the number of particles or constituents that the theory has is finite. Then you can, if you go to a very high energy above all the scales, and their number is finite, by the way, unlike string theory, this is the loophole for string theory, where there are always new particles, then you get the relation I said in the following manner. You assume that in a field theory there's no gravity involved, so black holes are not created, so everything is extensive. The only scale you have in your problem are the temperature and the box. So if you count the number of states at very high energy, it must be equal to the number of constituents times the volume of the box. And because the only scales available are the temperature and the length or R of the box, this exactly will be the amount of entropy. The amount of energy is calculated in the same way, except it's energy, so one needs to multiply it by one extra scale to get energy, and that gives you the temperature. Remove the temperature from these equations, and you will get that the entropy goes like the number of degrees of freedom at high energy to the power 1 over d, and then you get energy to the power d minus 1 over d. So this is the general argument why at high energies you should always get this dependence. Now, in recent years, there were arguments by Cassini trying to obtain in a more rigorous way various type of bounds, in particular what was called the Bekenstein bound. But in all those cases, you are not really looking at the high energy spectrum of the system. You're studying something else. And the bound there was just 1. And from the point of view of field theory, it's obvious that the bound is going to be 1. But there are issues about short distance behavior and so on, which I'm not entering in here. So take this. This is a derivation. It gives the correct result. But there are subtleties which one has to take care of. So this vindicates, if we go back and look at what the student calculated, this is characteristic for high energy in 10 dimensions, and this is characteristic of high energy in 4 dimensions. Now, you realize that such a system tells you that low energy people can be megalomanic, because they believe they live in a 10-dimensional world, while actually the number of dimensions is much smaller, by 6 smaller. And of course, we could also be in such a framework megalomanic. We think we live in 4 dimensions, but from such a point of view, maybe at high energies, our number of dimensions would be actually smaller. If that would somehow be the case, this would solve many renormalizability properties, many properties we have and think about at short distances. In any case, this is there, and what I'm, let's say in this year, I'm looking also for examples in solid state physics, because my experience in the past was that outside general relativity, usually most phenomena that we found in particle physics had the earlier counterpart in condensed matter physics. So I'm looking for solid state systems which had such crossover phenomena, and maybe they're there. I'm trying to see what characterizes them there. But that's part of an open problem, to try and find systems which are not GR-like systems, or not necessarily, maybe they do have to have a dual, I don't know, but when they start, they are not GR systems, which have the property that the infrared dimension is larger than the UV dimension. And I remind you again, for normal compactifications, the UV dimension is the higher one. Here it's the opposite. It's the IR which is the higher, and the UV is the smaller. Okay, here I do a fast calculation to remind you why a Schwarzschild black hole, why the entropy goes with the power of the energy which is larger than 1. So I use the Bekenstein-Hawking idea that the black hole entropy goes like the area. This is just to translate the Newton coupling in whatever dimensions to the string coupling. And then when you change the language and go to the language of strings. So strings give you, instead of the box, you get the scale, which is L string. You will find that the Schwarzschild radius is related to the energy by this power. You plug it back in, and you find that the entropy goes like the power of d minus 1 over d minus 2. And let's see here. D here is the number of space dimensions. You see from the calculation already from RS d minus 1, the d is not space-time here, so I'm sorry. In the transparencies before, d was space-time. Here, d just signifies space. Now, I make here a side comment which many people have emphasized. We know that we are lucky in order to understand physics, which we measured up to now, and not including quantum gravity, that scales are separated. So the fact that we are ignorant on what happens at high energy did not disturb us from calculating G minus 2 with an astounding precision, calculating the weak interactions with fractions of percent, calculating the strong interactions with percent accuracy, or some phenomena in each of these with this high accuracy, even though we don't really know what happens at higher scales. And we may never know. So the fact that scales are separated is very helpful. So when we look at galaxies or we look at atoms, we have a big separation of scales, and this enables us to work. Now, nobody owes this to us, of course. I mean, we could just be lucky so that we can use renormalization group, effective Wilson, Fisher ideas, and so on, but it is a very helpful thing. But somehow when gravity comes in, we have to take into account that this stops being the case. And I'll remind you on two ways you can see that. One point of view is, usually we expect that if you take a mass of a particle and its Compton wavelengths, then the higher the mass, the larger the mass, the smaller the Compton wavelengths. And that is true till we reach things which are black hole-ish, or Planck lengths and Planck mass. And we see that in this case, actually, the mass increases. And the object radius, the equivalent of Compton radius, actually increases as well. So the separation of scales stops to be so clear. And I remind you that the same happens also for strings. If there are compact dimensions, strings have winding numbers and have momentum modes. So their mass is related to the length of the compact dimension. by momentum modes going like inverse radius squared, but winding modes going like the radius. So for the objects which are non-field theoretic, but which are go like winding modes, again, the heavier the object, the larger it actually, the radius of it is. So this idea that we have separation of scales becomes more complex when gravity is involved. And this is something which time and again people think about. In any case, we see that for black holes, the radius, the Schwarzschild radius, increases with the mass, with the energy. Strings have random walk in occupation number. I just write this down. I'm not entering now into how this exactly goes. And when you add up, even though these objects are different than what we expect, we find that their entropy, I didn't write it here, is actually goes like the energy. So for a free string theory, without taking interactions into account, that you afterwards have to take interactions into account, the entropy goes like the energy. In particular, this means that the system has a limiting temperature. Now, maybe in one of the talks which will come, I will discuss in more detail if you cross that temperature a little bit or not, but asymptotically, you definitely, for free strings, you have a limited temperature. Now, if what I told you here about ADS CFT is correct, let's go here, then you see there is no limiting temperature actually in that system. Because when you reach high energies, the entropy goes like, the claim is, it goes like e to the 3/4. That has a positive specific heat. You can pump in energy, the temperature will increase. So there will be no limiting temperature. So here is a case where it would seem that in flat space you have a Hagedorn maximal temperature, but when you, in a system that you can study in detail, which is ADS, this bound on the temperature disappears and you can increase the temperature at will. Okay, here. Okay, so we are back here to this graph. I explained to you the e to the 9/10 and e to the 3/4 in retrospect, namely what I would identify from the student, what the claim was here, what the claim was there. Then the advisor probably also threw him out because how come it's field theory? Why should there be strings? And why should in this field theory, which has no gravity, there should be objects which behave like black holes from the term of the entropy? So these are all the reasons that this student disappeared. However, later on, once ADS CFT was accepted, even though it was never proven, but there are, let's say, a lot of indications that many aspects of it are correct, and we will see here how non-trivial these things are. This actually was argued in the opposite way. Namely, from the point of view of the phases of gravity, this is what you would expect. You would expect to have a phase of gravitons in 10 dimensions, because the string theory is 10-dimensional. You would expect a correspondence point where the highly excited gravitons actually turn into strings, and this is why you see that. Then there is another correspondence point where the string begins to form characteristic lengths which are like the Schwarzschild radius related to the mass of these objects. And that correspondence point relates strings into black holes. And then as you go on with energy, because you are in ADS, and now ADS is important, the black holes, and I will show them, in the beginning they are small and they don't realize that there is a curvature to the system. But when they become as large as the curvature, they begin to realize they are living in ADS. And in ADS, Gibbons and Hawking, okay, these are the transition points, by the way. If you They are calculated in a very naive way, but which is very powerful. You just say, these are the effective degrees of freedom. You build a cocktail. You say the cocktail contains in it gravitons. The cocktail contains in it strings. The cocktail contains small black holes. And the cocktail contains large black holes, which are Schwarzschild. For each one of them, you know how the entropy should behave. And you ask who dominates in this cocktail at a certain energy scale. And the words I told you before are related to this comparison of entropies. Now, this was very useful in gate theories. When one studies the phase structure of gate theory, the degrees of freedoms in the most general case would be dyons, objects which have both electric and magnetic field. I may again reach that later on. But the simpler objects, let's say, have just electric and magnetic charge, either that or that. And you can find out which phase the system is by doing, again, entropy arguments. So the key issue is, the key assumption is you identified the relevant degrees of freedom. And afterwards, you just do simplistic thermodynamical arguments. And actually, they were borne out by very sophisticated calculations going under the name Seiberg-Witten and what happened after that. So the idea is that you use this same type of arguments which worked so well in gate theories, use them also in gravity. And then these are the different transition points. This is when radiation ceases to be. This is when strings become small black holes. And this is when small black holes become black holes inside ADS.
What parameter needs to be small to have a separation between these correspondence, between these scales?
Well, as you see, you have here, there is G string, and the transition, let's say, point would be 1 over G string squared. So this is, you would need that not to be pushed too much to 0, then you would not see anything.
But n, because you have n and G.
Well, but Gs times n is lambda, okay.
So no, if we have two parameters, G
yes.
and lambda.
Yes, you have two parameters. Yeah, you have one parameter which is the 't Hooft coupling, and okay, I didn't say because that's part of the ethos of ADS-CFT that the geometry properties become more apparent when this coupling is very large, and then you do perturbation in string theory, which is the other coupling GS. Okay, now I want to take the graph we had here, and I want to write the temperature of the system. So if I write the temperature of the system, you see that I have positive specific heat for the gravitons, constant Hagedorn temperature for the strings, negative specific heat for the Schwarzschild black holes in flat space, and then positive specific heats for black holes in ADS, which was, again, the big surprise. This was found by Gibbons and Hawking long ago, and somehow it escaped, its significance escaped for many years, that these are black holes which have that property. Now, Gibbons and Hawking used them actually as an example of confinement, and I will discuss, we'll see where that comes in. Okay, so let's say we have this type of behavior. So when you do your course in statistical mechanics, this invites a Maxwell construction. Namely, you see that if you have a microcanonical analysis, which is what I've done, I've shown you the full information. But if you want to go to a canonical ensemble, you will actually jump and have a first order phase transition. You will go from the system here, which is a system of gravitons, of radiation, into the system where you already see only the 4-dimensional properties of the system. And the part which are strings and Schwarzschild black holes in flat space are transient. They will disappear. These phases don't materialize. In the canonical ensemble, if your temperature is your control parameter, you will go from one phase to the other, and this goes under the name Hawking-Page transition. And I will discuss it now from the side of the gravity. So the ADS metric, I'm going back after I told you what would be the consequences of the work of the student, which didn't exist. We go to the bulk side. On the bulk side, we have an ADS5 metric. And you see the R squared, which appears in the metric up there. And what actually Gibbons and Hawking were doing, they wanted to build a Faraday cage for energy. It is important when one studies such problems to be able to say there is a wall where you put the system and energy cannot pass through. But energy can pass through anything. So their way of building a Faraday cage, which you can in electrodynamics, but you can't in gravity, was to put the system in ADS, where the first component you can relate by, this is Euclidean, when you go to Euclidean, you can relate to a temperature. And you see that the temperature goes to 0 as the distance in ADS goes to infinity. So in a sense, you arrange that the system lives in a box by using this metric. And that was their trick of confining energy in a certain range. Or as you look here at the effective temperature goes like 1 over the square root of G00, and it's therefore this behavior. Then, if all the data you give us is that the system has a boundary which has a certain structure, then another object which has the same boundary is a black hole sitting in ADS, which I've written down here. And you see that when you take R to infinity, the boundaries are the same. They differ when R is of order related to the mass here. So these are two thermodynamic or two configurations which are solutions of Einstein's equation of motion. One can be viewed as thermal ADS, and the other can be viewed as a black hole in ADS. Now these are two solutions of the equations of motion. There is no general analysis, so we don't know what the most general solution of the equations of motions are. There could be others, and you will see that actually would be nice if there were others. Even though nobody owes us, you will see that the final description is like that. So these two different solutions are going to be the competitors of these two different phases, which I've shown here. What sits here is thermal ADS, and what sits here is the black hole. And the way you do it a la Bekenstein and Hawking and Gibbons, you calculate from general relativity what are the free energies of these two different objects, and you ask who dominates. Now, as I told you from the picture, we already expect a first order phase transition, which is what was found by Hawking and Gibbons for this configuration. And what actually happens if our conformal boundary is a sphere, S3 times a circle, which gives the temperature, then at small temperatures, there is actually no black hole. The black hole is singular. You could not close the black hole with a cap. It becomes singular. The black hole only begins to appear as a configuration, so as a candidate, once the temperature of the order of the curvature. So there is a phase which is just thermal ADS, because it has no competitors. Then comes the phase when the temperature is of the order of the curvature, when there is a competitor. But in the beginning, the competitor loses. The black hole doesn't win the free energy competition, but this is for an order 1 change in curvature. And eventually, when the temperature reaches scales which are larger than the curvature by some specific amount, it's a black hole which takes over. And you find out that the black hole is the dominant configuration. So the two phases which we saw here, just by this construction, actually materialize in the thermodynamics of general relativity that you do here. So you have the black hole, which I've drawn, and you have the cylinder, which is ADS. Now, once you look at this, you already find yourself involved in another question. Something that people asked without even having a good handle on general relativity is there a Klein paradox in general relativity? What do I mean? We know that when people realized that you have to write down a relativistic field theory, they realized that the number of particles is a good number conserved as long as there are no interactions. Once you have interactions, you have to have superpositions. Here the question is about topology. Namely, do you allow yourself to mix topologies which are different, or don't you? And maybe there's a superselection rule which says that once you live in a certain topology, there is no need for you to go to another topology. As I said, in Klein paradox, the question was, can you keep yourself content working with a fixed number of particles, or will you have to, there is no superselection rule once there are interactions, and you will have to have a superposition of the fixed number of particles you started your theory with. Okay, so what one finds here is that if ADS-CFT should work, you have to have the permission, the license to mix topologies. As I said, there is very strong indication that it is correct. I don't know of any proof that there is a hole in that. So if you take that as your basic point of view, you have learned that topologies have to mix. Why? How does this come about? When you look at the theory on the boundary at short distances, its entropy goes like n squared, where n was the n of SUN gate theory. When you look at the dictionary and calculate the entropy of the black hole, it goes like n squared. On the other hand, in the ADS part, there is no n squared. Everything is of order 1. So if you start and say the theory lives only in ADS, and there are no, I should not allow myself to mix a black hole because it has a different topology. Classically, it doesn't have a pi 1. It ends here. So classically, I don't see a pi 1. If I would not allow the black hole, I would get a contradiction, and I would have to give up ADS-CFT. Okay, so I mean, you may want to give it up. But the idea here was, I think this Edward Witten actually suggested, he said, okay, no, let's allow to change the topology. We know that in gravity the black hole would dominate, and the black hole gives contributions of order n squared. And the question which is really left open and not solved till the end, even though people conjectured about it, is, okay, we have here a behavior which we have shown in gravity. In the field theory, there was this imaginary student which diagonalized it, but the imaginary student left. So we don't actually have a diagonalization there. And here is a prediction that there should be, when you are on S3 for very large n, you should have a phase transition. But that phase transition, there were suggestions on what it is. I'm not yet familiar of a proof in the theory that it was there. In any case, this was a case where actually gravity taught us on the gate theory. Okay, so here I repeat, when the temperatures were much smaller than the curvature, there was only ADS. Anyhow, when the temperatures were of the order of the curvature, you had both thermal ADS and a black hole. In ADS, and when the temperature, actually there are two black holes there, one with positive specific heat, one with negative specific heat. In any case, it's the thermal ADS which dominates, and eventually it's the black hole which dominates. And these are the two phases of the theory. Okay, so keep this in mind. We learned something about ADS-CFT. As I told you, there are some open issues there involved. And now let's relate this information to the original question, which was, what can geometry capture? And in particular, let us go to the case of the black hole information paradox. Okay, so here the original work on this was by Maldacena, and the tools he used was ADS CFT, and the idea was to punch a hole in the arguments of Hawking. So the calculation that you can do in principle is the following. You're asking if there is a black hole information paradox or not. Okay, take some initial bulk state. So if you would know the dictionary, which we don't know, put it to be an initial CFT state. You know the Hamiltonian of the CFT, it's a field theory. Let it evolve. You will learn what the final state is. Go back with the dictionary, which doesn't exist, to the bulk and see what happens. So you can answer the question, how exactly does a state evolve? By going to the field theory. But as I said, this direct approach is still beyond us. One doesn't know how to, the dictionary is not developed enough to be able to do that. So instead, one looks at a different way to address the same issue. And the different way is, you take a system at thermal equilibrium, now the quantum field theory. It's true we think also about the black hole like this, and we'll come to it. But you take the quantum field theory, and you perturb it, and you ask, how does it react to this perturbation? What happens to it as time increases? So one considers a thermodynamic ensemble with some density matrix rho, and one calculates the correlation function rho AT, A of 0, and one looks at very long time scales. And one wants to see what that does. So if you look at this operator A of t, you can develop it by e to the IHT on one side and e to the minus IHT on the other side. Insert, as we usually do in elementary quantum mechanics, a complete set of states. And you will see that this function C of t is a sum of a density matrix times matrix elements times many phases. And the way this system will behave will eventually, it does depend on details. I think it's now appreciated more than it was appreciated 10 or 15 years ago. It does depend on the details of the spectrum. It does depend on the details of the operators one inserts. And I will show you what are the classes of results that one gets. Now, what does one know about such a correlation function? Now, there are theorems in the classical case. In the quantum case, I don't really know how strong the theorems are. Maybe people in the audience know how strong the theorems are. There are things which are done in quantum mechanics. There are some things in quantum field theory, and some are, let's say, common wisdom and intuitive. I don't know what basis of rigor they really have. So if one looks classically, and one tries to answer the question, what are the characteristics of this time average correlation function, then without entering first into details, which one should, how the spectrum looks like, how the matrix elements look like, one says the following. If the phase space is compact, and if Liouville theorem is true, namely you have a conservation of volume in phase space, if you are under the conditions which allow that, then if you calculate or let's say you are in some element of phase space, then there will always be a time t for which for any epsilon you will be in a distance epsilon from that volume. To do that in quantum mechanics, instead of the compact phase space, you need a discrete spectrum. Instead of volume conservation, you need unitarity. Instead of looking in where you are in phase space, you calculate some correlation function at time 0. And the claim is that any correlation function you have calculated at the time 0, there will always be a time t of p for Poincaré, for which the correlation function at time t of p will be different in value than its initial value by epsilon. It will always exist. This is the claim. So let's say people who are very conservative and say that they have seen it all, it could be true because you see it all. Or I don't know if in French you have Humpty Dumpty is part of the French culture. Is there an equivalent Humpty Dumpty? No. Okay. So an egg which falls and breaks will come back together again, contrary to what you teach in thermodynamics. So what is the way now to make this useful for us? So you look at a quantity g of t over g of 0 of some not too large correlation function. You take its absolute value squared, and you take its time average. So you take this quantity g of t over g of 0 absolute value squared, you integrate it from 0 to capital T, you divide by 1 over t, and you send t to infinity. Now, what will this measure? The claim was that the sink will return essentially to what it was. So that means that there are sinks which recur. The function cannot just go to 0. Now you want to measure with what weight this recurrence occurs, and it turns out it's enough to put a 1 over t. You don't need to put a higher power of t in order or lower power of t in order to see that actually the sink does survive. And I'll show you the claim how this goes, but the claim is that this quantity is bounded from below by e to minus a number times the entropy. It's not just minus the entropy, but it's a number which sits before the entropy. So this is a very strong statement, and you will see that in the context of ADS-CFT, it's a non-perturbative statement. It would be a statement which the lower bound would be 0 to all orders in 1 over n, but it's actually not 0 because it has a non-analytic part which gives this contribution. So what does this tell us? It tells us that our usual intuition that systems just thermalize, which would be just this exponential drop-off, isn't correct, because if that would be the case, there wouldn't be a lower bound. So that means things have to recur, and the question is, okay, what happens and how does this manifest itself? So right now, I want just that we keep in mind, we are speaking about gravity, okay? But now this is a lecture in quantum field theory. Gravity doesn't appear. It will reappear thanks to ADS-CFT. But for the time being, it's not here. Okay, so now you define a quantity, which is the noise, which is this average, the square root of this average value. Actually, we'll normalize it in a while. This is, again, I remind you, the quantity. So let's go and calculate it. So in general, if we take this object, take its...
I thought it was called G. The G is C.
This was... you caught it. No, it was called L. But still you are right.
It was the ratio, no?
Yes. And C...
C is L, is the ratio G of T divided...
Right. And this changed. This letter changed. You're right.
But now what does it mean?
The same, just L became C.
So it's the ratio G over T divided by G0.
G0 will... No, without G0. G0 will appear. Okay. Right now with no G0. G0 will appear in a slide or two. But thank you. Okay. And I didn't know how to change it, so that's it. So these are two different letters which have been identified. So we take this quantity and we average it, and let's take, to make things simple, let's take B to have, to get a feeling, no diagonal elements. Let B be a matrix where we have removed diagonal elements. If you want, you had an element, I think before it was called G, now it's called B. I could remove from it, write a new object where I removed everything from the diagonal. So in that case, it is clear that if the diagonal matrix elements are 0, then when I take the average, it will enforce that EM equal ER and EN equal ES. Because all other...
Average is with respect to time.
Yes, this is the line above is the average with respect to time. So in that case, when I would have gotten that C of t is that sum there, rho is a density matrix, so it's positive, and the square of matrix elements is positive. So in that case, C is actually positive. And you see from there comes the lower bound. In the case of general B, the things could fluctuate around 0. But this captures the feature that there is a lower bound. OK, so now you do an estimate. And I will show you a rough estimate. And the estimate gives you that you get here e to the minus s, but also actually in here can appear another number. So the main thing is the decay stops. You cannot just go down because you have to satisfy a lower bound. Here is a rough estimate. You take the matrix. This is now C on the maximum is actually C at t equals 0, and this is the normalization factor you asked about. And you find by analyzing the numerator and the denominator that the ratio you get here is of the noise, which will take a square root, would be e to the minus s. I leave you as an exercise I've given here.
It's a definition of S?
Entropy.
Yes, but it's a definition. You estimate S as a function of B and rho.
OK, so S comes out of the density. Let's say it would be a microcanonical ensemble. Then in the normalization of the microcanonical ensemble, S would come. The same in a canonical ensemble, it would be the same. I didn't complete here the proof. I invite you to look at the paper. And I will show you an example where S appears also through the objects B.
Here B disappears
in this here, but I told you things do depend on B. So B actually reintroduces, and I will show later on, I don't know if this today or next time, I will show a B which is related to the eigenstate thermalization hypothesis, where the matrix elements of B contain in them an e to the s. So where does, in other words, where does it appear? It appears in rho. It appears in the sum, because we are summing over states, and the number of states we have is e to the s. And it can also appear in the matrix elements B. So these are the places where the entropy emerges. And the final outcome is that it goes, the estimate in certain cases, like e to the minus s. Okay, that's the...
So the statement is that the Poincare recurrence time is e to the plus s.
Let's reach that. We haven't reached that yet. Okay. Here this was just a state of what is the average, what is the average noise. Okay? Then we have to see about recurrences, because now we are into averages. Mm-hmm. Okay, so first time, the first thing is, when you look at these graphs of how this would behave, the usual thermalization would expect that the correlation function drops exponentially. And it's actually when there are a large number of conservation laws, first you go to Gibbs general, you first remove stuff, and then after you go further, you get power laws even. But in any case, the thing goes down. But let's say there are not too many conservation laws, so the thing just thermalizes. So this would go, depending on the operator, definitely not universal, would go like e to the minus some gamma t. And because you need to reach an average of e to the s, the time when you reach the average is of order s. So the first time scale in the problem as formulated here is s. That is the time when the system begins to reach the average, and it cannot continue its behavior. Now, how intuitively do you look in the sum? You say that as long as t is smaller than s, or much smaller than s, then the spectrum for you is continuous. The Heisenberg uncertainty principle for time and energy, you don't yet feel the very discrete nature of the energy levels. So the exponential decay part is the time when everything looks to you continuous. And that stops when you reach times of order s. Now, the truth, and this is what I've written here, are Gedanken calculations. Of the whole set, I have not yet seen somebody really even doing a computer simulation showing that all these intuitive ideas are the ones which are accepted, are the ones which actually occur. So now, once you reached this value of e to the minus s, what happens? So there is a first time scale which we called the Heisenberg time scale, where the system begins to feel that it is a sum of many different, clocks. Let's think of e to the I alpha, difference of energies times t. Each phase is some circle and a point on the circle. So the clocks have deviated, and you begin to feel they're each its own frequency. How do you estimate that time? That time you look at a certain band you have. You say that the average characteristic time of that will be related to the average energy difference, because you have a sum over energy differences. So the average difference in energy will be related to 1 over the number of states in this discrete band, which means the time goes like the number of states. So this time goes like e to the s. This is not yet a time which is particular to you, because you can be much more particular than me once we decide which epsilon you need. You may want to have much smaller epsilons than I want to have. So this number here, e to the s, does not depend on how picky we are. It's just a statement that I'm going to feel the fact that I have some average difference in energies of the system. So I don't have things of order 0. I have things which are now e to the minus s there. Now, in order to be able to want to reach and estimate, so this goes on, and this is the Heisenberg time. And it goes like e to the s. Now you can ask yourself, okay, I look at this set of clocks, and I want, let's say, all of them together, I look at a global shift, to be within delta alpha angle where they were originally at time t equals 0, which was 0. And I want to see how long that takes. So how do I estimate? And now comes your precision, because delta alpha is related to how much precision you want. So you have this motion on a torus. Each clock defines a certain compact variable. The time it takes should be 1 over the probability, which is related to the volume. The volume would be delta alpha over 2 pi to the number of degrees of freedom. This should be a power, not a multiplication. So the volume to which you want to return is delta alpha over 2 pi to the number of clocks that you have. And you want to return in all of them. So that means that the estimated time goes like e to the number of degrees of freedom times the log of 2 pi times the delta alpha. And this is going to give you the Poincaré time, which will be exponent of s times the log of 2 pi over delta alpha. So if you don't care very much and you make delta alpha 2 pi, you're back to the Heisenberg time. But if you're very particular and you want really the delta alpha be significantly smaller than 2 pi, then you will have times of exponent of s. And then you will be really returning Not just that you are not zero and that you are there, but you will be returning to the original value that you had. So this is when the spikes will become of order 1. So these are 3 times. The time of the stop of the drop of the thermalization or whatever behavior. Then there is the time where you begin to feel the difference, the average difference in the distance of the energies. Of course, when the smallest gap gives you the longest time scale, the largest gap gives you the shortest time scale. You look at the average, and then exponent of S, you begin to return to where you once were. So here is how this would look under these repetitions in time. Now, it's interesting that all these times go, each is an exponent of the other. So you can ask, what is the log of S? Because we had S, e to the S, and e to the e to the S. And the log of S is related to something I did not describe and will not describe here, which is called the scrambling time, which is more or less the time it takes you to spread the information, let's say, over a horizon of a black hole using your calculations in the past. So that's another time, but I'm not using it here. But it's also related by a log. Okay, but I'm sitting here before Thibault, so you can't not put numbers. But you want to see what, okay, what does this give? So I'm afraid the natural unit is universe lifetimes. We'll call it UL. And let's look at S, not at e to the S and not at e to the e to the S. So the page time, this also goes for other reasons. Things of order S go under the name of page time. So look at page times of for a black hole the size of a proton. It's 10 to the 10 ULs. The page time of a black hole, which is 10 to the 9 solar masses quasar with 3 kilometers radius, is 10 to the 87 ULs. And this is just S. So one is talking here about something which science fiction doesn't dare touch. I mean, one is going to epochs which are enormous. So why? Okay, what's the justification of doing such a thing? So I will go back to phenomenology. Many years ago, Jean Iliopoulos and his colleagues were looking at something which was of no significance to most people, which were flavor-changing neutron currents. At the time, there was no nice picture of the standard model to most people in mind. So why concentrate on flavor-changing neutral currents and their absence? Who cares? And nevertheless, from that, they derived a deep understanding on what is the structure of the universe. In particular, that you need to have at least one more quark to complete the doublet of the strange quark. So here we are in a situation where we have a very consistent theory. And in a way, I would say that any hole you can find in this fortress of, I call it bastion of consistency, because that's our tools, we can't do the experiments as we discussed, is worthwhile. So even if there would be a problem after e to the S, let's identify the problem. And once there is a hole, maybe one can inflate it and help the fort crack. But maybe you will find that once again the fort reacts and doesn't allow you to have a problem. So the justification to going to these very long timescales is one is looking somewhere for a hole in the argumentation. Okay, so the summary, there are timescales related by log S. There is a scrambling time. There is a page time, the end of the decay. There is a Heisenberg time when you begin to feel the average distance. And then there is the Poincaré time when you recur to what you really started. So how is this related? And here we to the original problem we were discussing. Okay, so the way it is related is by doing the ADS CFT. And as I told you, the responsible adult in the relation is a CFT. So we know that if we do n equal 4 super Young-Mills theory on a sphere, the theory is unitary. We have no reason to suspect the theory is not unitary, no evidence of that. And the spectrum is gapped because I'm sitting on S3. So one is sitting in the conditions of a general conformal field theory. And there is a lower bound to the object at hand. It's there. Okay, this is the spectrum of states. Enter. The point is, there is a lower bound. The lower bound, and now I'm talking not about the general theory, but the theory at hand, goes like e to the minus s. This s goes like minus n squared, because we are in the joint representation. There could be numbers before, but it's minus n squared. This goes like e to the minus 1 over g Newton that appeared in the slide where I showed you the dictionary between the field theory and g Newton. That means that this is from the gravity point of view, it's non-perturbative. To any finite order in Gn, this vanishes. But for n large, and if n is infinite, it also vanishes. So you have to think of an n which is extremely large, but not infinite. And you find from the CFT, you know that there is a lower bound. And now, okay, you found it. Let's just find it also in the bulk. Let's go to a temperature which is well below the Hawking-Page transition. So we have the black hole. And let's calculate a typical correlation function inside the black hole, I mean, in the background of the black hole. And let's recover the lower bound. And here was the point that Maldacena emphasized, that there is a paradox. Why? When you calculate the correlator of two scalar fields in the background of a black hole, you go to tortoise coordinates. So you shift the horizon to minus infinity. And you find that the propagator can be calculated by solving a non-relativistic quantum mechanical problem sitting in a certain effective potential. And the effective potential characteristic is that it's Liouville-like as it approaches the horizon at minus infinity. So such a spectrum doesn't have a gap. So your ground to be sure that things will behave as you expect and that you get the lower bound, you lost that. You do the calculation and you see the reason that it was important to have a gapped spectrum. And indeed, you find that the black hole gives a result which is 0. So you can drop ADS CFT because you get 0 from the black hole, while you know from the responsible adult that there is a lower bound.
Here you are computing the correlation in time of a scalar around the black hole, and you say it goes to 0
Yes.
for large time.
Yes.
That's what you are saying.
Yes, yeah, quasi-normal modes, whatever words you want to use, but I used here because I used in the assumptions the fact that the spectrum was gapped. This assumption, once you have Liouville here, the spectrum is not gapped, so you lost the ground, and indeed you don't get that. So you get, if you wish, what you know, anyhow, the quasi-normal mode behavior. So you get an exponential drop-off. An exponential drop-off will give for the lower bound 0. Finished. A contradiction.
And there is a power law actually afterward.
Okay, but you get 0. So you can throw it depends, conservation laws or not, but you at the end just throw ADS CFT. Maldacena is proven that Maldacena didn't wrong. Okay, but it's Maldacena, so no. So then he's not US, so he took a non-US attitude, and he said, well, let's not concentrate only on the winner. We had two configurations, and I remind you there can be many more, which we don't know about, but we have two configurations. As long as the leading configuration delivered, then we follow it. But if the leader configuration gives us 0, we should go to the other saddle point. And the other saddle point is thermal ADS. So first, if one does it, once again, just like before, just calculating the entropy, you see that you need the change to have several topologies. You cannot live in a super selection of topologies. Okay, so in political correct language, you have topological diversity. You have to allow different topologies if this solves the problem. So you get out of the black hole and you go to thermal ADS, which was highly non-leading configuration. What characterizes in tortoise coordinate? How does the effective potential look? I described to you before, there is a box. And that's the characteristic of ADS, it's a box. So you get a potential where you have a box. And the box appears also near where was the horizon. It moved away, we have a box. And at this stage, you have a background in which the spectrum is gapped. And the gap is determined by the curvature of ADS. So now when you calculate the object, you are going to find that it respects the lower bound. So you see that a configuration which was down by e to the minus s was called to help when the leader failed, and it delivered. It gives the right answer. But it delivered for what? It delivered for the average. And I told you in the slogans in the beginning, geometry works for averages. So we had here an average which is extremely small. Exponent of minus s, I think you got an idea how small it is. So it's a very small effect. And nevertheless, this small effect can be reproduced by geometry. But this is the average. What happens when you ask, okay, here is, I will end in 5 minutes. And by the way, the lectures will be 1.5 hours and not 2 hours. That's the good news from today. So if we look, one way to think about this, we had a black hole, and then it suddenly becomes, as it moves in phase space, it suddenly becomes a thermal ensemble of gravitons. And
this was large black hole, suppose.
Yes, everything is large. I'm way beyond. Yes, I'm way beyond the Hawking-Page transition. I'm not discussing. We can discuss also what happens below, but I'm taking a thermal average way above the Hawking-Page transition. So everything is large black holes.
Not decay by Hawking radiation, it transits to thermal.
Yes, just I don't know. We like, okay, in some sense, instanton, tunneling, superposition, whatever your fantasy tries to build. And then the dissipation, instead of happening in the presence of the black hole, the dissipation happens in the presence of ADS. And this is somehow a type of attempt to see how these recurrences come again and again. However, if you look at the exclusive quantity, not the average, but you ask what C of t is at every time t, then you see that this cannot explain the problem. The geometry fails here in this way, because we knew it from the start. We know that Poincaré recurrences are order 1. Because we had to resort to the loser configuration to give us the peaks and not the zeros, it will be multiplied by e to the minus n squared, because the probability to be in it and not in the leading configuration is suppressed by e to the minus s. So what happens is you get an average by having short Heisenberg times. The recurrences happen very frequent, but the height of each recurrence is minimal. It's e to the minus s. While the true behavior should be large recurrences, which happen extremely rarely. And that we know from the quantum field theory. And both it happens, and it's very nice to see in detail, they give the same average, up to coefficients in the numerator. However, they don't give the same exclusive behavior. So we saw here an example where geometry gave an extremely small quantity correctly when we were talking about the average. It failed to give the correct behavior when we talked about this very minute behavior. So we see in here the limitations of this semi-classical description. It cannot, as far as we know up to today, it doesn't mimic the detailed behavior. And I think it's nice to see that coarse graining is given by black holes, more details are specifically ones are not reproduced, and I think it gives some meat to a general feeling, which I will give by another example in the next lecture, that indeed there is some coarse graining when we talk about geometry. And when the questions are very, very detailed, we have to resort to other stuff. Semi-classical geometry is not giving it to us.
But maybe we need a very special operator because here you have the generic operator, so
yes.
we don't know what it corresponds to in the bulk. So maybe there are operators that measure something geometrical and are something very special in the CFT that
it could
not proven.
No, and well, there are many things proved which I haven't shown and things I have not proved which I didn't show. But I would say that the idea, if geometry is a description, it should be generic. There never is a claim. I mean, also averages, if you wish, are something non-generic. And we decided to pick an average and then geometry works. So there is no doubt that there can be quantities for which geometry could work. But the idea when you use geometry is not that you have to look out of e to the s properties, find one property for which it works. The idea is what happens generically. So I think the idea here would be that for generic objects, averages do work, but more detailed, exclusive misses, and you can see by how much it misses. Now, what was one way we suggested out, and maybe this will at the end be, we said, okay, so this reminded us like in QCD, people were trying to find what is the configuration which will lead to confinement. And it didn't happen at the end, and it's a more complicated phenomena. So maybe that looking for the average for the ADS and having also the black hole is just the tip of the iceberg of many, lots and lots and lots of stories you could tell geometrically. And when you sum over all of them, maybe they look like 't Hooft's brick wall. Because if you do put a brick wall, a firewall, whatever you want to call it, you can arrange so that you get also the exclusive CT for every T. You can do it. The problem is that, and this we show in our paper, but the problem is you don't know a priori from the string point of view what is the width of the brick wall. You just impose, there exists, and for the theory there exists a brick wall for which it will reproduce C of T. Because of course it produces a gapped spectrum. But what is it, in order to have a real understanding if that's the right way, you need to get it from the string theory side. You have to get a width, and then you have to show that that width actually corresponds to what you get from the QFT. So there is a way that there would be many configurations, and the sum of all these configurations would effectively be a black hole with a brick wall, so that you gap the spectrum, which was again the idea of 't Hooft, maybe others, how to get a gapped spectrum. Okay.
Also to get the factor 2 wrong in the working spectrum.
Okay, but here the main thing is to get the gap. Okay, that's without that there is nowhere to go. Then we do the next of the details. But the first thing to make the continuous infinity into a discrete. That's the key thing you need to do. Okay, so the conclusions of what was done. Maldacena punched a hole in Hawking's argument. He showed, because his arguments of Hawking did not include the possibility of changing topology. So now the burden shifted, and other people may have picked it up or not. And I think one is still discussing this issue. Topological diversity is required. Without it, it won't work. I also would say that the fact that even it works for the average, for such a minute quantity, shows you how difficult it is to breach this hole in the wall of the consistency of string theory. We have not yet succeeded in doing it. And these are the slogans. And for next time, I will start and continue, because one question which would come out would say, okay, what did we have here? We had here a very strange situation, that the long-time correlation function's behavior was dictated actually by the thermodynamical disfavored configuration. Is this generic, or did it just happen by accident in this case? And we will start by addressing this and relating that to the ER equal EPR paradox. Okay, I will stop here. And thank you. I will repeat some things which I said last time to give a general framework. First of all, I'm discussing problems which interest me now, but one of the features of them is that they are not all prepared and packaged in a well-defined way. There are loose ends, and there are problems which some we have already seen, and some more that we are going to address as we go along. The general theme which interested me here is, what does semi-classical geometry capture? What type of phenomena? And what is the fate of singularities of various types in string theory? The general tool one uses is the ADS CFT framework, where in this duality type arrangement, actually the responsible adult is the field theory, and we try to extract as much information as we can from the quantum field theory in order to be able to extract various interesting qualities about what happens on the string theory side description. But in a sense, the QFT is a definition, or the non-perturbative definition, of the string theory side, up to maybe some loopholes which appear. But this is a general point of view. And I will repeat that most of the work I describe here was done with José Barbón from Madrid. Okay, so we spent quite a lot of time discussing field theory and correlations in field theory at large time. And I didn't enter, I will now, but I did not enter into the details of what precise two-point correlation functions I am calculating in the field theory. And it will turn out that the result depends very importantly on what these things, what these operators are. Now, in retrospect, it will come in a few slides, we will see that for chaotic operators, and I will try to define later what I mean by the chaotic operators, if one calculates a two-point function in a field theory which has in it a discrete gapped spectrum and is unitary, then there are some general features one can say. The first feature is that depending on which precise operators are chosen, there is either a power-like or generically an exponential decay in the beginning. However, a certain correlation function which we defined, which was the time average of the thing written above integrate time average, taking that value squared, normalizing it by its value at 0, has a property that while it starts up at order 1, by definition here, it reaches a certain lower bound around which it can oscillate a little. So I would say it's not a precise lower bound, but it gives you, it is precise for the average of the square. It's not precise lower bound for the thing before being squared, but before being squared it would fluctuate around that average lower bound because it would have to reproduce it. So one has a decay. One begins to feel the fact that the spectrum is not continuous after a time which we call the Heisenberg time, which is order of the exponent of the entropy of this system. And then after a time of exponent of S, one approaches, which is called the Poincaré time, one approaches the original values to whatever precision you actually want. Now, the fact that we took this particular operator, and this Thibault asked me later, okay, so you took this operator, it's an operator, it's a local operator on the boundary theory. What does this correspond to in the bulk? So the general idea, but it was never proven, it is part of the, let's say, dogma in the field, which people are trying to probe and understand, is that the behavior of this chaotic operator corresponds to the behavior of a local two-point function in a background of thermal anti-de Sitter and in the presence of a black hole in anti-de Sitter. So the claim is that the way one captures the, let's say, black hole-ish or near black hole-ish properties of the system comes by this operator being chaotic. And the precise details of how locality is matched are not known and are not taken into account here. Now, we found out that if one looks at this correlation function, which is the correct answer calculated on the boundary, and compares it with the bulk result at a temperature in which is a temperature where a black hole dominates, let's call it the statistical ensemble, that is technically called beyond the Hawking-Page transition, which I described last time in some detail, how to construct it, how to Maxwell construct it, etc. Then there is a paradox, because in the presence of the black hole, calculating such a thing in a bulk would not show a lower bound, but this, and the average quantity would go to 0 instead of being bounded from below. Now, the remedy for that, for the average, was to suggest that one has to recall the other stationary point in the problem, which was the ADS, thermal ADS background. And I explained why in calculating in a background which is thermal ADS, the average correlation function behaved exactly as it was expected with the same numerical values as what one got from the field theory. So one is relieved that the ADS CFT correspondence worked, and one learned en passant that you have to take in the bulk theory at least two different topologies, which was always a question. Does one take the same topology? There is super selection rule which sticks you with one topology, or should you take several ones? And I also remarked that actually before this is due to Maldacena, there was at a higher level, it was shown that if you don't take the black hole when you take thermal ADS as a background, and you forget the black hole which has a non-zero, which has a 0 pi 1, unlike thermal ADS, that you would again get a paradox. So these are two places independently where you needed to define the rules of the field theory so that you should at least take all fields which are solutions of equations of motion which have the same conformal boundary, even if the topology, when you look at the whole bulk, is different. So these were the various lessons that we learned. And then we learned that if one asks what happened at any particular time t, we totally miss the picture. Namely, we cannot reproduce by the thermal ADS, which does reproduce the average. It does not reproduce the more exclusive property, which is how the correlation function behaves at each time. So we learned that geometry can produce very small e to the minus s effects when they are averaged in one particular example. And on the other hand, we have seen that it did fail to get more exclusive properties. The simple geometry of just taking the two solutions didn't work. We discussed what happens if one tries to take more solutions. I won't repeat it now.
But does one, for instance, get the correct value for gamma, the decay time, as a quasi-normal mode?
No, because gamma is totally not universal. Gamma really depends on the details of the operator. The e to the s and the e to the s to the s, so on, these are universal. They only depend on the fact that this is a chaotic operator. On the other hand, the particular value of gamma does depend on which operator one puts on. And as one does not know the exact correspondence between the bulk and the boundary, this exercise, I mean, you can do it, try and do it case by case, but you don't have a general picture like you have here. And people look at some specific cases, but the picture is not general. And we ended up with a question, which I will answer today. Was the failure of the thermodynamically dominant contribution to reproduce the average, we defined quantum noise was the average value of the square of this operator, was this an accident, or is this something which would occur in general in certain, I mean, in general under certain assumptions as usual? So again, the conclusions was what I wrote before, and that at that stage, the burden of proof that a well-defined information paradox exists shifts to the claimer, that topological diversity is required, and string theory is quite a formidable bastion of consistency, because we did succeed to extract e to the minus s effects, which are not very easy to extract. So this is a summary of what we did in the last talk. Now, the fact that the burden of the proof shifted back to the claimer didn't mean that somebody won't lift the ping pong ball and shoot it again. And indeed, after this set of works have been done, another attempt to claim that the theory isn't well formulated came through claims that for various reasons, which would require a set of talk on its own, which I will not do here, is that actually whoever volunteered many years ago to parachute into a black hole just to see how he crosses or she crosses the horizon and to enjoy the experience, would actually never enjoy the experience, would be boiled, and it would meet when they reach the area of the horizon, would reach a firewall where the temperature would be ill-defined, would be infinite, and the object would just boil. This has led to lots of exchanges in the literature, and from my point of view, the problem has not yet been formulated sharply enough to be able to decide one way or another, even though there are many people which would not share this opinion. But this is my own opinion. So I will concentrate on one particular round in this fight. Is there a firewall? Is the horizon something special? Or is the horizon, like we would think from GR, something that you could just cross using the equivalence principle as your insurance policy and nothing would happen? Or is this fallacious? And I will take one particular aspect which follows the theme which we discussed here. What does geometry capture and what does geometry miss? And this goes under the name ER equal EPR. ER is Einstein-Rosen, EPR, Podolsky is added to this. And the claim is that the various paradoxes, several of the paradoxes which were brought up, which led some to conclude that the simplest solution would be a firewall, other solutions would be more radical even. the problem gets resolved because entanglement issues can be related to the existence of Einstein-Rosen bridges. Again, it's very nice to discuss it. I won't do it here. I will just discuss the particular element in the controversy which relates to the theme we're discussing. So there was a paper by Maldacena and Susskind which said the following. Let's take the arguments that a group of people, Amhari, Marolf, Polchinski, and maybe the younger guys would remind me, I'm missing somebody starting with M, okay, or S, okay. Sully maybe, paradox is just not there. So they say, let's consider an eternal black hole in ADS. There are very good indications that an eternal black hole in ADS and its dynamics can be described by a product of two disconnected conformal field theories, each living on one boundary, and writing a maximally entangled state which would reproduce the geometry and the excitations of the geometry of the eternal black hole. And the state would be the following. Here, by the way, in field theory 1, the Hamiltonian and time, they have the same Hamiltonians. In one time flows this direction, and the other times flows in that direction. And each state here will correspond to some story in the bulk. So the state they take here is the maximally entangled state. They diagonalize each Hamiltonian. Then they take the product of eigenstate of the Hamiltonian n of field theory A, which is identical to eigenstate n in field theory B, and you multiply it by e to the minus the energy level appropriate for the state n, and you divide it by some temperature T, where this temperature T will define what is the temperature of the eternal black hole. So if you want to build a black hole of temperature T, this is where you put the parameter T. And the claim is that all the physics here would be the physics here. And in particular, if you look at this object, it has no firewall. So this is a situation which in principle would be one of the examples used by people who claim there are firewalls. And they say, look, here is a counterexample. So the debate did not follow about the counterexample, but about the genericity of the counterexample. The claim was that this is a very atypical case. And then Marolf and Polchinski suggested, okay, here I just remind you that if you look at a one-sided black hole, that is, you integrate over the other field theory, you will get a density matrix which will be appropriately describing the black hole. It won't play now any more role. So the arguments of Polchinski, Marolf and Polchinski was the following. Say, okay, you took a very special state, which was a maximally entangled state. Why don't you take a state where you have a general NM structure here with some general matrix GNM, and not insisting that this is a delta function. Look at this state, and now calculate the two-point correlation function which we discussed before. And then they said, okay, we learned in the past how the two-point function behaves in the presence of geometry. And this is what I described to you. It starts being of order 1, it decays, and then it reaches its average and jumps around the average with, from time to time, big jumps and mostly just very small fluctuations. And they said that if you calculate the noise, let's call it, in this configuration, you will not get this behavior, which we saw before. That was the claim. You will not, and the emphasis was here. They claimed that you will get that the height of this correlation function is of the order e to the minus s. You never reach a 1. So it's not something which at least is known to be reached by a geometry. because when you look in the either black hole or thermal ADS, you get a totally different behavior. This will give you a different behavior. So for a generic state in the quantum field theory, you will not have a geometry, and therefore you cannot argue that everything is smooth. You just don't know what is going on there. You cannot ascribe it some particular configuration and say, look, here is a very unsingular, near the horizon, geometric configuration. Because the noise calculated on the quantum field theory side does not correspond to anything that we know about geometry. And maybe there is something new about geometry, but then show it. But it's not our experiences in geometry. Okay, so this led to a second round of looking in more detail in all the questions of the behavior, the long-time behavior of the correlation functions. And in particular, a point maybe was known to people, but let's say when I spoke about it here many years ago, definitely was not appreciated enough by me, is that the observables you choose and the way how representative they are for the dynamics has a great influence on the results. So the things I showed you before, and I emphasized work for chaotic operators, are not true in general. One should really revisit this and study this for each type of operators. Now, in particular, as I told you, the common wisdom for what would represent successfully and give you features of black hole physics in the bulk, the claim was, are chaotic operators on the boundary. And the chaotic operators were defined in the following way. They are supposed to be the representative operators. Again, doesn't mean there are not other operators, but they're supposed to be not representative. So how are the chaotic operators defined? So this is taken from things which were done many, many years ago in, let's say, fundamental quantum mechanics and statistical physics. It went under the eigenvalue thermalization hypothesis, eigenstate thermalization hypothesis. And the argument goes the following. They say that a general operator, which would be some Hermitian operator, does not commute with the Hamiltonian. And moreover, if you look at the eigenfunctions of this operator, they are highly uncorrelated with those of the Hamiltonian H. And these are the operators which you should measure their time dependence. And to be more specific, the claim was that if you look at that unitary matrix, which takes the operator, the generic operator, B, in the basis of energy eigenstates, and you diagonalize it, so capital B is in the eigenstates of energy basis, small b is being diagonalized into the basis where its own eigenfunctions, that the matrix which does it is a pseudo-random matrix. So if you do this, if you make this assumption, so it's a strong assumption where you say you have a feeling on what is the right physics. And as I said, among the open, the loose ends, and people are working it from many points of view, is to give more and more basis for this foundation. Foundations to this claim. I will now just take it and show you just what are the consequences on the structure of a representative matrix B from this definition, from its definition. So the claim is, and I will show it, that a typical matrix or a representative matrix has some diagonal form. This is again written in the basis of energy eigenstates, on which there is nothing special to say. And then it has an off-diagonal form where you have some smooth number, small b, which multiplies it. This b will relate, of course, the eigenvalues you have. This is written between an eigenstate of energy En and Em. And this is how you define E bar and omega. So this is some number which has no special characteristics. Then you get that the typical length or magnitude is of the order of e to the minus entropy over 2, which is a strong statement. So these are very small off-diagonal matrix elements, but they exist everywhere. Because this object here is supposed to be a random matrix of absolute value 1. So it's some e to the I theta, where theta is random. So this type of matrices are supposed to be the ones where one does the calculation. So how does one get this result? So in a very crude manner, let's look. The matrix U must be unitary, and by the assumptions that it's essentially all eigenfunctions of E participate in one eigenfunction of B, you get that each matrix element, there are e to the s matrix elements, so each matrix element must be of the order e to the minus s over 2. So this is now the U. B, the off-diagonal part of B, is U, some number B, U bar. So this would be a sum of e to the s elements of some random, because of their character, their product would be e to the minus s, because each is e to the minus s over 2. But then you don't get e to the s of them really summing together coherently, but because of the random nature, it's some random walk, and you get e to the s over 2. So that's how you end with this b being of the order e to the minus s over 2, and multiplied by some other stuff of order 1, which is random. So this is the picture one has, and as I told you, these were ideas borrowed by Asher Perez and Deutsch, Srednicki, from many, many years ago. So now one does, given that this is the matrix, which is characteristic for a black hole, what you should ask, what you should use when you ask about systems where black hole should be there, then, or for the system of n equal 4, that's the claim, you do the calculations with that. Now there are many type of calculations you can do, and I won't do all here, I won't show you all. There are some where you do the noise when it's one-sided. The EPR noise is, of course, when you have you're looking at noise, as I showed you, of a state Nm with a matrix G and M between them. What noise do you get there? Then you have what happens, we'll discuss when there are several bands, and also when you have a system which is quasi-integrable. Okay, this is just to show you now that you can do various things. You get various results which depend on many considerations. I'm not going to enter into all the details. I'm just going to give you the results that we are interested here. But I just want to show you, because it was a lesson for us, that there is a lot of structure involved in which operator you choose to take, and what state do you take as a state you are interested in the system, which is a conformal field theory. Is it diagonal? Is it untangled? Is it pure? Is it mixed? All these things change, and each one gives different results for the noise. So now let's go back to the original claim. So Maldacena, Susskind took the diagonal state. They said that is the state. You can go ahead and calculate the noise in that state. And of course here there is no horizon at all. No singularity, no sign of singularity on the horizon. And you get the same result as I discussed last lecture. So this all looked very geometrical and very non-problematic. So we have the value of the correlator itself before being normalized is of order 1. It's characterized by the geometry, and the noise it gives is of the order e to the minus s times some numbers which I didn't discuss anyhow. Now let's take the state which is non-diagonal and ask what happens there. So you can ask what is the value at t equals 0, or in general, what is the maximum value that you can expect this to give. But taking the lessons of last lecture, you can also ask what is the average noise that this produces. So if one looks at the first question was the one which was addressed by Marolf and Polchinski. Look at the correlation function and try to identify its maximum when the matrix were the ones that we have discussed. And I remind you that Mn as these random, there was e to the minus s over 2, which was multiplied by the order 1, but random phase which appeared. So when you look at this correlation function, you get this normalization structure. Then you have, because you're summing over n and m, you have these number of terms. You have these which have phases, and you have this torus of, let's say, e to the s dimensional torus, which we can build from En and Em. Now, it is clear that each of the phases here is ergodic. So you can try and use part of it to remove the phase structure, the random part of Rmn, which you have for the general state. However, there is only an exponent s of such independent phases you can use. And you need, in order to make this of the order e to the s, that is to make all this sum coherent, you need e to the 2s terms, and you can't do it. So this won't help you. And what you end up is that when you look at a random walk structure here, you have only e to the s elements, which means that the maximum that this will ever give you is e to the minus s. And therefore, for a generic state in the conformal field theory, if you try and calculate what does it give, you don't get the geometrical picture, which is at least somewhere this was of order 1, and it repeated itself, this order 1, many times, very sparsely, but it was there. Here you cannot get it. Because, again, the argument, you have here a torus of phases, but these are not enough phases to get rid of the random structure of R and M. However, if you calculate the noise, that is the average value of the correlator, you do get exactly the same result as you got from the diagonal maximally entangled state. So this is another example of geometry, in this case, let's say, eternal ADS, which was really corresponding only to the maximally entangled state, giving you the correct, the exact and correct, giving you the correct average quantity. The average quantity was calculated by the geometry, very good. The moment you want to change and look into more detailed structure, like what is the maximum this has at a certain t? Is there a t for which this be order 1? The answer is no. Indeed, there, Marolf and Polchinski stated correctly. This doesn't look like a geometry when you ask a very exclusive question. But if you ask an integrated question, you get the right result from the geometry. So this is example number 2. And as I said, we show that it does not depend, the noise, the average noise does not depend on the entanglement. Then this is just a remark to people which were more concerned with this problem and aspects of it, that if you want to get an order 1 amplitude, which I showed you is not what you would get e to the minus s as a maximum, you need to have a state-dependent conditions. And indeed, some solutions of the problem of the firewall came through the direction of changing a little bit how the rules of the game are, and say that some of the particular things you measure depend on the state where you are doing the job. You're doing the measurement. So indeed, never mind you actually know that this is what would diagonalize in field theory A, this is what would diagonalize in field theory B, this is the random part on matrices A and B. If you have a particular relation between the matrix elements, then for this specific operators, which is again type of question you asked me, Thibaut, before, but these are operators which are, let's say, more interesting because they are space dependent, state dependent, because they depend on the matrices omega you needed to use for the diagonalization. If that is what happens, then you can arrange for coherence. but that's not the generic situation. So to conclude what we got here, up to now, we had two examples where geometry gave a number which was very small, the noise. It was e to the minus s. It's non-perturbative from the point of view of the gravity theory. It should be 0 to all orders in perturbation theory. And nevertheless, geometry can capture it. But if you ask a more exclusive question, like how does it behave at any time t, geometry fails, doesn't give the right answer. Maybe eventually a way will be found, but as of now, we don't know. And the question could be so murky. I was using it as an analogy when people first thought that you could solve confinement by instantons in 4 dimensions. It didn't work. And then people began to look at various configurations. One of them were called Mayrons. And one started to invent more and more rules to try and get the result you want. But it ended up as a very murky subject, which actually did not lead to any concrete conclusions. And it could well be that the attempts to get exclusive information out of detailed semi-classical geometry will also end up being very murky. Maybe some nice structure will emerge. And I mentioned, let's say, the issue of the brick wall or the stretched horizon, which maybe by some way can effectively describe the sum over all kinds of things which are murky. But that's where the status is today. Averages of very subtle and small quantities are given by geometry. More details, geometry doesn't know how to give them, but you know the result from the field theory, but you don't know how to reproduce it from the bulk. At least there's not a clear calculation which produces them. Now I want to go back to more details about this. In particular, I'm interested in the detail. Was it accidental that the low energy band that was thermal ADS dominated the behavior of the system and gave us the result we wanted? So here we take a matrix which has two totally, let's say, different structures in terms of number of states, which is characteristic of n equal 4. I showed you that there are actually 4 bands. Let's start just a moment, just look at 2 bands. So there is one where there is a lot of states, very high, and there is one band where the number of states is very small. And the claim is that generically it will be that the low energy band will dominate. And how does this work? So assume there are a few bands. Okay, the system, it could be that the system doesn't have at all a band structure, and breaking it into pieces doesn't make sense. I tried to argue last time, and I will show again the graph in a few minutes, that in the system at hand, it does make sense to look at several bands. So the calculation I'm giving here, the estimates I'm giving here are in the case when it makes sense to look at the band structure. So if there are several bands, there is a probability that you will land in that band, and then there is the type of noise that you will produce if you are in this band. For example, when we go back not to the field theory with the bands, but we think about the bulk picture, there were 2 configurations. There was a black hole with a certain temperature, and there was thermal ADS. And each one was given with the weight of the free energy corresponding to the Gibbons-Hawking calculation of the free energy of that system. So for a general object correlation function, you will give the probability that you are there, multiplied by what happens if you are in that band, what type of behavior you will get. And when you do this analysis, you expect, as I said, the probabilities will be related to the free energies. And the noise, we estimated how noise should behave, and noise goes like e to the minus s for the time being. We are looking about chaotic operators. So if we look at that system, we see that actually if we take the noise and we multiply it by the probability, which is a free energy, we get exactly the Boltzmann distribution, which will tell you that the low energy band will always dictate the level of the noise, the average noise. So this, it's a simple argument that was missed before, and it explains that the fact that the thermodynamic dominating band did not give you the noise is not accidental. It's always the lowest energy band which will give you the maximal weight for the noise. That's statement number one. Now let's look at a case where the system is quasi-integrable. If the system is quasi-integrable, the relevant operators to calculate are not these ETH operators, but in that case they are clearly operators which are a few field excitations. That means there are some combination of A and A dagger if you have some quasi-particle picture for that. So you can calculate what is the noise, not of an ETH operator, but an operator which has this structure where the coefficients here are given by what you would expect, the Bose distribution in a system of which is, let's say, quasi-particle excitations. And the result, which let's forget here the calculation, it's not important for me now, the result is the following. You would get that the noise is much larger. It goes like 1 over square root of the entropy. So it's not the e to the minus s or s over 2 effect. It's just 1 over square root, having a much larger noise. So this is, again, to realize that when you do an ETH system and you look at its like long time behavior, when that is a characteristic operator, you get a very small noise. But if you are in a system which is nearly integrable or has lots of conservation laws where a quasi-particle, a free quasi-particle picture makes sense, you will get a much larger amount of fluctuations, a much larger noise. And that goes like 1 over square root of s. Okay, one can do the same for the EPR noise, and I emphasize again that the representative dynamics picks the representative observables and has a big change on how the result looks like. Okay, I will come back to it. Here I can just say this is the type of field theory that we discussed in the ADS CFT. So this is on the CFT side. There are several bands. I told you these are gravitons, 10-dimensional. These are strings. These are Schwarzschild black holes in flat space. And these are Schwarzschild black holes in ADS. And there is this 4 bands that are expected from the bulk side. Okay, it would be nice to get it, of course, from the boundary side. And here is what we discussed. Depends ETH or black holes in strings. You take the ETH, and for the gas you take operators of the form that you discussed, which look like quasi-particle. So now you can do the calculations in these 4 bands. And here I will just give the final result. So if you look at the noise at a temperature which is much larger than the Hawking-Page transition, so where the black hole dominates the thermodynamics, each of the bands gives a certain answer. From here you get, from the graviton gas, you get the 1 over square root of s. And you get the various pieces, and you find that, again, which is the leading one, and you get the same type of answers that we got before. It's the low energy which determines it. In general, you can say that the average noise is determined by the lowest band. The fast variations are also determined by the low energy band. On the other hand, the height and the long time variations, which I show here, the long time variations and the total height, they are actually determined by the leading thermodynamical configuration. So if you would be listening to ADS, you are part of NSA, you listen to ADS, you know which are the pieces which you can associate with the low energy part, which dictates the average noise, and which are associated with the various time scales in the problem. So the conclusion of that part is geometry produces correctly the average property, which I would say now we have 2 average properties given correctly by geometry. It reproduced a very small non-perturbative result. It does not reproduce finer details of the non-perturbative behavior of the time-dependent correlators. So that's where we stand here. Slogans, I repeat, diversity counts, geometry captures what I said. I think this is just repeating itself and just making the slogans clear. Okay, now you want to, do you think a 10-minute break would be good now? Or I go on? What do you say? Okay, so from now on, your responsibility is that we go on. Okay, so now I want to take a different diagnostic tool for the system. Before, I have discussed long-time correlation functions as a diagnostic tool. Now I want to discuss complexity. Now I will define complexity, I will discuss classical quantum, and I will calculate various properties of complexity of singularities. And we will try from them to learn what do singularities behave like. In particular, I'm telling you already now that some singularities will have a property which reminds you of things which Thibault liked to work, that is of systems where when you approach the singularity, you find a decoupling of different points in space-time, and you actually have like a strong coupling lattice system that is a very low degree of entanglement, and you just have each object obeying its own quantum mechanics. And similar things will, or ideas, or locks like that will come as a result of this analysis. But first, I need to define the complexity, what are its expected properties, and then what happens in the presence of singularities. Now, I emphasized in the beginning of the first talk and of today's talk that there has to be a responsible adult in the analysis, namely that one needs to understand how the quantum field theory works. And one has to have precise quantities and well-defined quantities in the quantum field theory. For the long-time behavior, this was the case. Here, this will not be the case. That is, even the quantities defined on the quantum field theory side have loose ends, and there are things one doesn't really understand in the definition of this complexity. And it will become apparent where the loose ends are, and hopefully eventually these will be closed. I think it's a very interesting line of thought. This was developed, I don't know, by, let's say, Daniel Harlow, by Lenny Susskind, by Steve Schenker. Many people, let's say, in the Stanford group at one time or another spend a lot of time to push this thing forward. They concentrated on analysis of black holes. Here I will concentrate on the analysis of singularities, and we will have various types of singularities to analyze. So let's start with a definition. How does one classically define complexity? So here is a definition, and I think there are no precise, when we go to the quantum case, there are no precise data on how universal the statements are. Because the statement will depend on various inputs. And it could be that some features of the result depend on the input. I will tell you what is not expected to depend, but I don't know if there are theorems which validate that. So first, you're supposed to start with a simple initial state. A simple initial state means not highly entangled state. So you take some physical state, and this is a reference state for you. And again, the question how universal the answers will be and how much they will depend on what you picked is, I think, to some extent open. Then comes the notion of simple operations. I will give examples of simple operations.
Are we in the CFT here?
We are doing some classical system in the beginning, and then the examples will become precise. You will see how to go on. So simple operations, I will give an example of a simple operation. Simple operations are supposed to be, if you have a state, it's given to you. Then you make operations which are changes either at one point of this, which defines the state, or at a small neighborhood of that point. and you have a small number of these simple operations. Could be 1, could be 4, but a small number, much smaller than the number of degrees of freedom you have in the problem. And then you define the complexity of the state as a minimal number of operations you need to construct that state from the initial state. So here is a concrete example. Let's say that a state is defined by, if it has, there are S points in the state, and it's defined by being 0 or 1. And if you want identify, you can have an overall Z2 identification or not, is up to you. A simple operation is that at one moment you take either 0 to 1 or 1 to 0. And you have S sites. Okay, is that? S will be like the entropy because you have essentially 2 to the S different states in this Hilbert space. So the log of it goes like S. So it's essentially, S is here, you should think of the entropy. Now, the maximal classical complexity for this particular problem, where this was the initial state, this were the operations, this was the system, is proportional to S, the number of sites. Is that okay, Thibaut? Is that precise enough? So now, okay, so this is the classical entropy of the system. When you do quantum mechanics, things become much more complex, because the state now is a sum with complex coefficients of states. This is now the most general state of which you want to calculate the complexity. A general state in the Hilbert space, and remember we want now to give each state in the Hilbert space a number which will be its complexity, is 2 to the S or to the K or whatever number you want, lattice points you have here. And you have to tell all coefficients alpha I, okay? So you can be happy that there is one phase and one normalization. But this is irrelevant relative to the large number of information you have to give about the system in order to know what it is at all. So the manifold of pure states requires ab initio, but in the definition, requires an epsilon resolution. Because this is a continuous manifold. This is the manifold of possible states. So there's no meaning of a minimal number of states, because that's a discrete notion. So what you need is first to already ab initio, on the field theory side, impose a resolution E, and then you can ask what is the minimum number of steps, and you will define what steps are. They can be, let's say, if it's a spin system, this could be 4 types of sigma matrices that you allow sigma plus to act on, let's say, 2 sites, sigma minus to act on another 2 sites, sigma 3 just to measure. You pick a set of operators and you move on the initial state, and you ask what is the minimal number of operations you have to do in order to bring it into a region epsilon of the state that you want to determine its complexity. And that's the best you can do from the start. So that's why I told you that the problem of definition starts in the beginning, but people do it. People try to do this game, and the answer is, and I'll give some intuition to how you get it, is that there is a bound on the complexity. This was shown by Kitaev and the collaborator, whose name now escaped me. Maybe you know who was. No, but okay. These are it's a 2-author paper, and the claim is that the complexity goes like e to the s times log of 1 over epsilon. And this is important, that the resolution epsilon factorizes out. So you can identify a piece here which is epsilon independent, which is e to the entropy. So the claim is, if the total number of states of the system, let's say, is of the order e to the s, this is the maximal complexity a state can have. And we will see it's not as I mean, the answer may look trivial, but the consequences are not so trivial. And remember, it's very important to remember that this is not, I mean, we all think of the Hamiltonian as or the transfer matrix as something which takes a state in time when it's not an eigenstate and moves it in the Hilbert space and tries to cover the whole Hilbert space in this motion. But that would not necessarily give the minimal number, the time it would take for a Hamiltonian of a system to get to the state we want to measure the complexity of is not necessarily the best shortcut. And this is one of the issues here, are for systems, what is the difference between the minimal number of steps? What is the time it will take to the Hamiltonian to do it? Is there another Hamiltonian where the time to reach the state minimally would actually be the time it takes a state to go from initial to final? And this structure of this is studied. Please.
Yeah, if the Hilbert space is the tensor product of n copies of plus minus.
For example, it could be an Ising model. Let's make Ising model.
So
yeah.
The dimension of Hilbert space is 2 to the n. Then what is S?
S would be n.
N still, okay, S still would be n.
No, not the Hilbert space. This would be, no.
The dimension is 2 to the...
The number, again, the dimension of the Hilbert space is the dimension of this object here, because you have all the, remember, I don't know how it's called, a Bloch space, I think. Sorry. You should remember it has all the alpha i's.
Yes.
Okay, and that's what dimension. So it's a dimension.
Okay, yes.
So the dimension you should take here, this is e to the s times e to the s minus 1 over 2, yeah.
And that space is CP. CP is projective.
Yeah, indeed. But okay, but the projective gives you, I mean, okay, so it reduces by 1. That's because, as we know, there is a total phase which is not important, and then there is a normalization, which is the other one which comes here. But basically, the large part comes from this. I mean, this cannot change. That this is e to the s times e to the s over 2. This is really the enormous dimensionality of that space. Okay, so if we look at that space and we put cells, then this is the number of, if you wish, that's an estimate to help you what you were asking. We have 1 over epsilon e to the s pieces, cells in that space. We have at each step of the order s choices to make. So in n steps, one can reach s to the n states. I act once, twice, so these are the number of states. Assuming no repetitions, I don't get stuck at a fixed point or something of that nature. So the complexity is bound from this. You see that the complexity is bound by e to the s. And that is the result that one gets here. Okay, now let's relate. This is the statements which I told you are not sharp enough because we don't know the dependence on the initial state. We don't know how universal it is. The hope is that if the state is simple, then most simple states would give a very similar definition to a complexity of a state. It's not clear exactly which operations I would do and how many operations I'm allowed to do simultaneously. How large, if I have the state, on how many elements should I work simultaneously. In quantum computing, these are called gates, and you have various gates of the system. Again, the belief is that if the state is simple enough, that is, has a the original state has low entanglement, and the operators that you act are local operators, and their number is much smaller than the number of sites of this lattice, then the results are more or less universal. This is the feeling, but as I told you, it's not much sharper than that. Now, how would complexity go for a black hole? And I will discuss we'll discuss that. So the idea was like this. If you have a black hole, its complexity in the beginning grows. Now, unlike the case we discussed before, actually here nobody knows in the bulk why the complexity stops growing. But we know there is a bound. So
In the beginning, what happens to the black hole? This is not
the part, I will show you the pictures.
the initial state we're talking about.
Yeah, so this, let me reach there. I will show you the geometry. Here, let me state the results, okay? And then I will show you the geometry which corresponds. You calculate various maximal volumes, and I will show you what that you will see exactly what it corresponds to. So in the black hole case, there is a period of linear increase of complexity, is a belief. It reaches, because of the bound, which you know from the boundary, it should reach a bound. At that stage, it's not clear how actually, what object that exactly will be, because we don't know the mechanism which will give that bound. And then, because of the Poincaré recurrences of the system will repeat itself. It will go down, go up again, go down and go up. So I didn't show you the intuition for this result. I will show in a moment. The time scales here are similar to the ones we discussed last time. It reaches a maximum time of the order of exponent of s, because the assumption is that more or less the complexity goes linearly with time. So the time it takes for this to reach such a situation is e to the s, and therefore the complexity, this would fit the bound. And then it would go down again. Now this reminds us very much to the thing we had before, but in the inverse. Before, what we had is, we had something which dropped down. Here we have something which increases. It reached a bound. Here it reaches an upper bound. There it reached a lower bound. And then it repeated itself. Here we more or less understand how the lower bound, what is the source of the lower bound, and what is the source of the continuant structure. In the case of complexity, at least for me, up till now, I don't know what the mechanisms are supposed to be. Now, from what I understand from quantum information theory, it is expected that there are regions where such a system would indeed, as I said, the dc dt should be constant, and c should increase linear with time. This t is temperature, it's not the time. And this is more or less given by dimensional arguments. And the claim is, and this is now a claim which one has to check, the claim is that the way to calculate the complexity is by taking the maximum volume, and I will show you of the system, and I will show you what is the maximum volume, how you define it at a given time. So here is now related to your question. So you start with a black hole. In ADS, this is all this thing. Otherwise, there's no connection to the CFT. So it's
This is a small black hole. It's a large black hole.
at this stage a large black hole. Okay, this is large black holes, and the temperature is above Hawking page. Okay, always. So there are no small effects which occur at temperatures which are lower than the curvature of the system. It's complicated enough like this. So you take it where the system is supposed to be simpler. That is, look at the temperature above the Hawking page. Then you start, this is the diagram which describes the hole, and you define the complexity in the following way. You take time on both boundaries to be the same. You could take them different. It doesn't matter. You could keep one of them fixed and let the other increase. That's wouldn't change the characteristic of the results. So given, let's say, the same time here and there, even though the calculations are done also for independent times, so you could have a TB here and a TA here. So this is anchored. Now calculate the volume of the various sections which are anchored on these 2 points. So there are many of them. Choose the maximal one. That will give you the complexity. This is the claim of what is the right thing to do. And the reason it goes to infinity. Yes, that's a problem. So I told you one does not understand how, unlike the case that we had before, where we understood the lower bound and its source, in this case, at least as far as I'm concerned, maybe some other people figured it out, it's not clear how a semi-classical picture will describe the saturation. Now, why did this come? How did this come about? What were the motives of Susskind et al. In proposing, in looking into that and proposing it? Because it's a proposal. It's not something that I mean, it would be great if one could really prove that and do the exact mapping from the boundary to the bulk.
But so what is again the statement? Because, I mean, all those slices have an infinite volume, right?
No, you always remove. Okay, so that's why you asked about ADS. You always remove the infinity, and you are interested in the increase. You are measuring the increase. So you take the reference volume, you throw it away. Sorry, I should have said that. Okay, so you throw away the reference volume, and then there is something which increases, and that's what you want to focus on. You're not interested in the constant, you're interested in the first derivative.
It comes from what?
And it comes from, in the bulk, from the fact that as the time moves up, the extremal surface becomes larger and larger. So here it was like that, here it goes like that, the opposite. Okay? So what were the motivations? Where did they come from? Why associate this geometrical object, which you know anyhow at a certain stage you will violate a bound, so it can't work all the way. But why do that? Well, there were several arguments. One argument came from the ideas of using tensor networks to build space-time. And when you use which is another subject on which actually I'm not an expert at all. If you do these, you see that the time progression of building increases the complexity of the system in relation to its volume. So this was one of the motivations of why people wanted to associate this with that, with the increase, with the complexity. The other reason is this is more or less here, when you cut it, this is the length of the Einstein-Rosen bridge. And people wanted to understand how do the Einstein-Rosen bridge increase in time. It's originally not its volume, but people thought about the length. Now it was clear that the time scales involved here were totally different than the thermodynamical time scales. Because as we saw, thermalization is of order S in the system, or maybe even log S, but definitely not higher than S, the page time which we described. While the times associated with the Einstein-Rosen bridge increasing are e to the S. So that was another motivation to try and check if the volume will follow that. And the volume did follow that. Now I don't want to, I cannot argue accept this intuitive claim and see what follows up from it. Why this dictum is correct, especially because the authors several months ago changed the dictum. And they said that instead of having here a volume, they want to calculate the action on the classical, what they call the Wheeler-DeWitt wedge of the classical action, which had the same, actually, for black holes, had the same or very similar properties as the volume itself. So as I told you, we are here on territory for which we don't have the established and clean definition on the field theory side, because we don't know all details of universality of the definition. We don't know where, for example, the quantity epsilon, or again, I don't know right now, where the quantity epsilon would appear here exactly. In the calculation, the epsilon was crucial in order to make the cells on the field theory side. Where this epsilon appears in the bulk is not very clear, but remember that the whole point of Kitaev bound was that the entropy part can be isolated independent of the epsilon. So it's probably sitting in some coefficient multiplying it, but it's not important from the point of view of the S dependence. The S dependence was like e to the S.
I'm confused. On the undefined field theory side, we are talking about thermal states. No?
We are calling about the complexity, and we have a temperature, and this temperature take to the black hole.
Yeah, but we have no time dependence. I mean, the complexity should not depend on any notion of time.
It does. That's.
Because this is an eternal black hole. I mean,
No.
I'm confused. This is an
Okay. Sorry. Maybe I jumped here once.
If you create
No,
a black hole,
let me. You asked the question. I give you the answer. So forget now the black hole. Think of the field theory.
yes.
Okay. So now, the field theory, we want to map the whole Hilbert space. There are many ways you can map the whole Hilbert space. You can go and pick your trail and go in it. But one way to map the Hilbert space is let the Hamiltonian develop the system. So take a state, which is a simple state, and at each time t, if it, I beg your pardon?
A pure state.
Not a pure, I don't want an eigenstate of the Hamiltonian. If it's an eigenstate of the Hamiltonian, I won't get, it's not a good way to be a tourist.
Pure.
Yes, pure, but not eigenstate of the Hamiltonian. I get a well-defined state. I let it evolve in time first. I can afterwards do a thermal average of it. That's not the point. The point is I let it develop in time. As I develop in time, I reach every time a new state. I ask, what is the complexity of that state? Okay, so that's where you get this thing. But you have to remember that the complexity of the state could reflect a shorter, a smaller number of operations than the Hamiltonian that took you there. So you let the Hamiltonian evolve it. So your first jump would like to say, the complexity is just related to the time after I change the units appropriately. It's the time it took me to reach it. But it's not, because that is not necessarily the minimal number of steps that you would have to do to reach the state. And the minimum number of steps is not defined by the Hamiltonian. It's defined by some other quantity, which is simpler than the Hamiltonian. So this is how the question of time dependence of complexity comes in. And this is why you know there is a bound, because eventually, once you cover the whole Hilbert space, it's over. You're not going to get that it takes, whatever you get, the highest complexity took you to reach a state after you covered the whole Hilbert space with your time, you're not going to get anything more than that. But you also have the issue of Poincare recurrences. So that will follow, you will go to states which have lower complexity as you move on. But the existence of the bound is clear, because there is the most complicated state given a certain epsilon. Is that helpful?
And if I'm in the Heisenberg picture, does it change the idea of complexity?
You will find, so you will do it with the operator. So you will ask how many, this is much better for mathematicians. You would have some matrix and let's say some unitary matrix, and you will ask by small unitary or emission matrices, how many times do I have to multiply to get the matrix which Heisenberg gave me? So both pictures should give you can ask the question in both pictures. It's a question of if you want to act on the state or want to act on the operator. Okay, so as I said, in the bulk, it's conjectured to be the maximum value. And it comes actually with one more statement. And the statement is, which you could see here, and that's why it became more interesting. The state was like this, and it was born by calculations done when you add perturbations to just this development described here artificially, if you wish, but well defined in the presence of the black hole. You can also add shock waves and see what happens when you add shock waves to the system. And the claim was like this. If you have a system which is thought to be the black hole, where complexity increases then there will be no problem at the horizon. The horizon should be non-singular. If, on the other hand, you have complexity decreasing, then the horizon would be singular. And very proudly, they show that in this case, there is no problem because the complexity all the time increases, and therefore there is no singularity on the horizon. And they did examples by adding a shock wave. So they could see where you could have a singularity, but then with a small thermal photon, you would get rid of the singularity. And because it would shift enough the horizon so the system could develop without any singularity involved. So they gave a lot of examples in the context of black hole physics that it makes sense to think that indeed when complexity increases, there is no singularity. And the wish here was to say there is no firewall, because in this situation, which has some generic properties, you actually have complexity increasing. And as I said, the things which are unclear, what exactly corresponds to the complexity on the conformal field theory side in the bulk? What is this mechanism which stops the complexity increasing because it must reach a maximum? So is there a semi-classical picture? Maybe there isn't. But is there a semi-classical picture which will say this stop? The advantage is that you introduced here an extra time scale, an extra object which happens, an extra mechanism which happens, the increase in time of the Einstein-Rosen bridge, its length or volume, which is not a thermalization scale. All this happens way after thermalization has been reached. So if you made a perturbation, you thermalized, all this happens way afterwards, because you have time scales of the order e to the s.
Anyway, I'm confused by something else.
Please.
This is time symmetric, so if I start at the bottom, the complexity or whatever will decrease to a minimum and then increase.
No, well, what you would say here is that you reach a singularity. So this,
Singularity is up there and down.
no, but here what they would say, by the time reversed thing here, that's for them an example of why in the presence of a singularity, why complexity decreases when a singularity is there. Yeah, that's for that one, but there is a white hole somewhere here.
And another question, if I thought one was supposed to have reverse time.
But remember, we didn't even reach here the horizon, forget the
If I
singularity.
take slices that do like this, they will always have the same Einstein-Rosen bridge, no?
Again, what you need is, you can do, and they did it, take a general TB and a TA, and analyze how things behave as a function of
If
T.
I do this, I have always the same cut, and there is a symmetry.
If you use boost invariance, so okay, but that's a very particular case.
But this is the natural thing, no? T minus.
No, I don't see why the boost case. I mean, the boost case is the one where you will see the invariance, but
Yes.
you want not to see the invariance. The whole point is not to see the invariance. So it's right. You can arrange, you will get a function of TB minus TA, and you can arrange, use the boost, you can arrange whatever you want, but the generic case, take TA and TB and just let them vary each one independently, you will see the complexity increase. Keep one fixed, keep the other fixed. So,
But if they are correlated, then it's even.
oh, again, the issue is not finding things which won't do that. The issue is to find something which will measure it. And they suggest they want to measure the quantity. They want to measure it, and they suggest that this is the quantity which will measure it. You are suggesting quantities which will not measure it. Okay. But they know that complexity changes in time on the boundary. I think this is clear, independent of universality issues.
What is not clear to me is that if the state on the boundary is not, I mean, if it is a thermal state, a barythermal state, and everything is an eternal black hole inside, then okay, nothing depends on time. I don't need to ask this question.
Yeah.
So now I need to start making some action indeed in the CFT to create
Yeah.
to start with a simple state, and then it develops in something complicated that thermalizes, but then it won't be at all a black hole like this in the middle. No, it will be something else. That will be totally
No,
dissimilar.
why? That's what I said. They do perturbations. They can do perturbations around this.
Yeah, but this is a bad thing to perturb around, because if I have a big thermal state and I add a little bit of things,
I don't know. Look, let's discuss afterwards. I don't. Maybe I don't understand exactly what you say, but let's discuss.
I would understand.
No, well, let's. I have 5 minutes, so let's discuss afterwards. It won't. We won't now converge to that. Okay. Well, with 5 minutes, it could be also a moment here. Where are we? Okay. So they give they give motivation on why they want this object, and as I told you, anyhow, it got changed. But I think the motivation is not empty. It's interesting enough, and there are interesting enough questions to pursue which are not clear, and the problem looks very similar as 1 over the problem, the S-dual problem of the long-time correlation functions which have a lower bound. Here you have an upper bound, very similar type of behaviors. They calculated, according to their definition, what happened for black holes. And what we calculate is what interests us for, and this I will discuss the next time, what happens in the presence of singularities. And we will do the same calculations, but we will do them for various singular backgrounds, including the Kasner case, including other cases, and I will describe what types of singularities one is interested in. And maybe I will, so, and of course we can discuss next time if you want more of the motivation of the group, why they think it's an appropriate thing for complexity. What I want to end now is actually something which I will use the blackboard just to amuse ourselves, because I'm going to use this for next time. But there is nothing yet to erase, but there will be. Okay, so we all know that in quantum mechanics, with the potential x to the n, there is no perturbation that you can do. You're familiar with the fact that if you have this system, you can always...
And it's even or?
This is the issue of a ground state, but for the problem I'm going to mention, it could be anything. You can always turn this into a problem where you have the energy scale sitting here, multiplying this by 2 operators which come with an equal weight. So that means that perturbation theory means nothing for this problem. You know the harmonic oscillator, and here you would get h bar omega as a function of the Hooke coupling and the mass of the particle. And this is general for any n, almost. So that such problems in quantum mechanics don't have any perturbation. You cannot make perturbation. All the relative couplings do to you is give you the relevant energy scale. Now you know there are many arguments you can say where perturbations, these are not bounded, neither operator is bounded. So if you take m to infinity, it doesn't mean that expectation values of p won't grow to infinity. So maybe it's not just a classical problem. And if lambda goes to 0, you don't know that if expectation value of x to the n will not contra this simple lambda dependence. And maybe, but without all this, you just do a simple rescaling, and you get that this is the case. Now there are 2 cases where this is wrong. So let's say one case where my statement was wrong and one where you can do a trick. So the case when my statement is wrong, I want to discuss. That is everything I told you. If you do the exercise of rescaling, you will find it works as long as n is not -2. If n equals -2, you cannot do the trick. namely the coupling which would appear here for n equal -2 is a real coupling in the problem. This can also, if you want, be an example of an anomalous dimensions in quantum mechanics, because things will depend, behaviors which you do by scaling arguments would suddenly depend on the coupling. And this particular problem, which is of the form p squared over 2m plus, let me take, in general, if G is positive, the system is, I will describe its properties, but it's well defined. If G is 0, it's a free particle. If G is negative, I don't remember the normalization, but G in absolute value, when G is negative, in absolute value, it must be, I think it's 1/4, but maybe it's 1/2. I don't remember. It's one of these numbers. 1/4. And beyond that, this is not a self-adjoint operator anymore, and you really introduce by hand a singularity at the origin. But as long as this is not happening, in none of these cases will you have a bound state, and the system will behave the way in the following way. So let's take G positive. In the case where G is positive, you have a potential, actually, if it's one-dimensional, then the space broke in two. If it's more dimensions, then it's just the radial part of it. But let's take one dimension. So this system, you can solve exactly. Of course, like in a free particle case, you won't have anything in L2. But you will have, for any energy E, which is larger than 0, you would have states which are plane wave normalizable. But for E equals 0, you will not have a plane wave normalizable state. The state will be, its normalization will be worse than plane wave. And therefore, you have a very interesting system. It is, the spectrum is continuous, bounded from below, but does not have a ground state. If you wish, time translational invariance is broken in this quantum mechanical case, because you don't have the lowest energy state of the system. And it's interesting what properties the system has, and I'm going to use it in the next lecture. So I wanted to introduce you to it. I will also mention again, there is now something more fashionable. This is something which was discussed from my point of view by Sergio Fubini, De Alfarlo, and Furlan many years ago. I did the supersymmetry case with Fubini, but the main structure is already there before you do the supersymmetry. And this model is called conformal quantum mechanics because it has a symmetry which contains, you have the operators H, D, and K. I will discuss them. The operator H, the translations in time. D, it measures the scale. And K is the special conformal transformations. And this is just xp plus px. And this is x squared. And they close on an SO2, 1 symmetry, which is exactly the conformal invariant. So it's a very interesting system. Now, recently, in recent days, months, people are looking for another type of system, which is called, related to the name Kitaev again, from a different point of view. And they're trying, instead of having this model, having here a Schwarzian derivative. Here you have just x dot squared over 2m. They are trying to use a Schwarzian derivative and get another type of conformal model. This I will not discuss, but that's now part of ADS-CFT. It's, let's say, a hot topic of research. I will use this model in order to discuss possible how singularities behave in string theory using ADS-CFT. So I think by this I exhausted this lecture. And we remain, I will maybe prepare for Thibault for the next lecture. I can review in more detail the motivations of Susskind et al. If you want. That's it. lucky that Thibault is actually here. And as Thibault was complaining that there are not enough calculations on the blackboard and just ideas, and he wants to see the calculation part. So I have in anticipation that he may be here nevertheless today. So I actually, the lecture is going to be in two parts. The first half hour I will do very fast. I will highlight points which I would have done in greater detail to conclude the series of 3 lectures. But the other part, 1 hour, is going just to be about anomalies. I'm going to discuss anomalies, how you have global anomalies, how you have local anomalies, and do specific calculations which I think are instructive. And there, in everything else I told you, there are open problems also there, but the area is much better studied and much better known than here. So what were the things that we passed through in the 2 formal lectures? We discussed that semi-classical geometry captures 2 averages which are very small and are of the order of e to the minus s. One of them was, well, both of them were related actually to noise. One of them was related just to the behavior, the long-time behavior of a 2-point correlation function. And we discussed chaotic case and integrable or semi-integrable cases. We saw a large variety of possibilities for the value of the noise as a function of the entropy. And we saw that semi-classical geometry gives correctly these very small numbers. We saw, however, that semi-classical geometry fails to give more exclusive information, in particular, how the correlation functions behave at any given time and not just averaging there. So this appeared once about 10 years ago in the context of black hole information paradox, and reappeared in the case of the ER equal EPR paradox, where once again it seemed that geometry may not play a role, but actually we have seen here the geometry can capture a very small quantity, which in this case was related to the EPR structure of various objects, in particular eternal black hole. And then deviations from that, and I won't go into any more. Then I said that I would like to study more about singularities. Of course, also the black hole has a singularity inside it, and of course also the firewall is a singularity. But I wanted also to discuss other type of singularities. Now, we know that in string theory, singularities which are time-like actually are resolved from time to time. There are examples in string theory where such singularities are resolved. And in a way, and now I don't know how the camera can do it, but you should close your eyes. And I will tell you, because I don't want you to see as I flip through everything, and I'll tell you when you can open them when I reach my target, okay? So my advice is close your eyes. If you insist on keeping them open, your problem. Okay, so I wanted to reach here. Actually, that's true. I want ones to reach there. And we know that in string theory, any concept that we know as unambiguous when one probes nature by point particles has an example where it becomes ambiguous, or if you wish, symmetric, that's a nicer word, when you probe nature by probes which are extended. The earliest and most famous one is just simple distance. You would think that if we have one dimension which is compactified on radius r and one on radius 1 over r, that the two are totally different. If you do quantum mechanics of particles on these objects, the spectrum is completely different. When you do string theory, that is not the case. And as you know, that is a tip of the iceberg of a class of symmetries known as T-dualities, and there is a whole group, very long structure, a lot of it penetrated into mathematics under mirror symmetry, and there are a lot of ambiguities of that nature, an infinite number of them, discrete infinity of them. Then we have examples of theories where the target space has different topology, and nevertheless, string theory would give the same answer. We have that for small cases, and we have it when the things are small. I won't go through all the examples, we don't have here the time, but just remember that if I write down a WZW model on level 1 on a certain group manifold, then I can describe it either by the group manifold, whose dimension would be the dimension of the group, or I can define it on the Cartan subalgebra, which dimension is the rank of the group. So you have here an example of A, the topology being different, because the topology of U1 to the R is different than the topology of the different groups, and the dimension is different because it's dimension G in one case and R in the other case. So we have this concept of topology ambiguous. The number of dimensions we know is ambiguous, large or small. In the first lecture, I spent time about how 4 dimensions with a certain set of degrees of freedom can describe 10 dimensions with another set of degrees of freedom. Then you can go on and do commutativity. We know that we have examples where for a certain set of degrees of freedom, we can consider the system on a manifold which is commutative, and for another set of degrees of freedom, the manifold is not commutative. You can look at associativity. There are examples in the presence of fluxes where the manifold may be associative or not, and you would get the same answers. And then you go to singularities. So the simplest case in string theory, when it's small, you take a C equal 1 model, you look at a circle of a certain radius, or you look at an orbifold of a different radius. The orbicircle is just the, okay, here I don't have, but you can use your imagination, just take here. You just let the target space contain a piece in it, which is a circle where you have identified the angles theta and minus theta. So by doing that, you have objects which on a circle were open strings. If you attach them to these points, they become closed strings. And they produce a twisted sector. You can study the whole model. But the main thing is that this object has, of course, 2 fixed points, at 0 and at pi. So this is actually the line with these 2 fixed points. And this object has a time-like singularity in quantum mechanics. However, you know that when it has a certain radius, it is exactly equivalent to a certain circle with another radius. So that is already one example. Then there are other examples which are more sophisticated, which I won't enter in, where you go into certain points, you generate extra massless particles, and then you have a different type of topology and different type of singularity structure. So actually, I don't know of any concept in mathematics which has not become ambiguous or symmetric when there are at least examples of where it has become ambiguous or symmetric in the presence of extended objects as probes. And I think that's very interesting. And I think it's a great pity that we don't have a unified picture of that, but each case we solve on its own. While I would imagine that eventually mathematicians would teach, or we would teach them, or they would teach us, how to have a unified picture which explains how come all these ambiguities come out. Now, as part of these ambiguities, I would like now to look into cosmology. And I would make here the claim that one can look on a cosmology which seems to have no singularities. Time goes from minus infinity to plus infinity. And you just lie on your, how do you call it, hammock, and that's it. Nothing ever happens to you. And on the other hand, you have another dual frame in which you have a drastic end of time, and in which there is a catastrophe, everything explodes. So you have two different pictures of the same phenomena in the bulk. So this is a very interesting thing, and we studied that with José Barbón in quite a lot of detail to try and understand how come it is possible to have both these pictures. Now, we know that in general, when we do singularities, and when we study singularities in a normal theory, the fact that they appear in our theory is a reflection of our ignorance. We don't know that there is quantum mechanics. We think about classical physics, and we miss that there is quantum mechanics. We miss massless excitations. But when we increase our knowledge, these singularities are not there anymore. General relativity is a trickier object because it has in it horizons. And under the skirts of horizons, maybe some things can be hidden. It goes, as you know, under their general principles, which are not, again, proven from anywhere, but you impose very general censorship issues in hope that such things are, all such singularities are always protected by horizons. But does it have to happen? Does it not happen? This is not obvious. And there are a set of examples where this actually does not happen. Namely, you can show that using, again, ADS-CFT as a tool, that there is no need that the singularity be there. So the way I distribute the half hours, I want some things to remain with you. So one thing I want to remain with you is this picture of the multiverse. So you have here various islands. In this case, the islands where we can live. And one minimum could be better than the other. And we try somehow to jump from one to the other. And in this case, I also capture the idea that, OK, you also want to live on the other minimum. Now, in general, when you have a field theory, which has two minima, with no gravity, then we know that there is a mechanism by which you go from this minimum to this minimum. And this was analyzed by many people, and by the Russian group, by the US groups. And the mechanism actually comes a little bit, even the intuition from statistical mechanics is, okay, let's say you are sitting in this, you have a wave functional, which is concentrated around this state. You try and stay there. Now, this is not an eigenstate of the Hamiltonian. You must, if you just write here the wave functional with no components here, it will not be a wave functional, an eigenstate of the Hamiltonian. And then the idea is that suddenly a bubble of the true vacuum will appear. And the question is, will this vacuum, will the revolution succeed or will the revolution fail? So this is an attempt to make a revolution. If it will, the bubble will increase, the revolution will be successful. If it will shrink, it will fail. Now, how does the analysis go? We know that if you create such a bubble of the right phase in the wrong phase, and I'm not talking, no gravity involved, then you are in a situation where you gain energy proportional to the volume of the system, but you lose energy proportional to the derivatives that you have to pay for if you go from one phase to the other phase. And here I took what is called the thin wall approximation, where it's very drastic and all the derivatives are concentrated here. You can also make them more blurred and do analysis on what happens. In any case, one effect goes like the volume, and one effect goes like the surface. So this means that there will be a revolution which will succeed. It could be that if the bubble which forms is too small, it will contract again. But eventually, there will be a bubble for which, no matter what the parameters of the problem are, let's say some phi force theory, so you have lambda 2 and lambda 4, no matter what the parameters are, this is going to, there will be a fluctuation which is large enough and it will take over, and everybody will be, the whole system will move to the other vacuum. So this situation of tunneling from one vacuum to the other is what happens in field theory, and it's not unexpected because both of these actually live in the same Hilbert space. There was never a doubt that the state here is just some excited state of what exists here. Now, what Coleman and De Lucia studied what happens when you add gravity. And when at the time the cosmological constant was supposed to be 0, so the question was what happened when the vacuum energy was larger than 0. Now actually what is interesting for us is what happens when you tunnel between two vacua, both of which have, let's say, a negative cosmological constant, because we are using ADS as a tool. In that case, what you see is not what you get. And the main reason is, let's say you are sitting here or even here, and you ask, am I stable or not stable? So in ADS, there is a major feature, as you know well, that the surface and the area and the volume scale in the same manner. So once you know what the parameters of the model are, you can't have a victory by having a very large, going to a very large scale. The issue of if this will work or not work is just determined by the parameters. So you may sit in a vacuum here, but in that vacuum you will nevertheless not go here because the parameters are such that it doesn't allow it. There is also what is called the Brighton-Mueller-Friedman bound. Even if you sit at a point here and you think you have a tachyon or an unstable direction, if the tachyon doesn't have a large enough mass squared, you will also be stable. But what is important for the discussion here, what happens is that generically, unless you do very fine tuning, and this was shown in the paper of Coleman de Lucia with calculations, that if you go from here to here, you crunch. It's not that you will now go to a new vacuum, no matter how many victims you had, but at least you settle in a new vacuum. No, you crunch. So crunch means that if you do the semi-classical calculation till the region of validity of your calculation, it seems like you're forming a curvature singularity. And afterwards, you're outside the validity of the calculation, and you don't know what happens. So ADS is a very good place to try and study what happens when you have singularities inside, and what does the holographic theory tell you about it, because the holographic, this is the words I said, because the holographic theory contains the total non-perturbative thing. Here I mentioned that in flat space, a large enough bubble will always beat the surface. In ADS, no. It depends on the parameters of the problem. Sometimes it will, and sometimes it will not. And then we went, again, I advise you to close your eyes. We made a setup in which one can study this. And one particular case is you can take the ADS space and make a de Sitter foliation of it. And when you do that, you have inside here somewhere a crunch in the Lorentzian part. I don't have, again, time to go into this diagram in detail. It just you start with the Euclidean part, then you build here the Hartle-Hawking wave function, and then you move from here to the Lorentzian part by doing the analytic continuation. And again, I invite you to look at the papers for all of that. The bottom line, in the time I'm dedicating to it, is this system, which it has ADS in it, and has generically a singularity in here. It consists of gravity, matter, and matter has an OD, 1 symmetry in the Lorentzian part, and OD plus 1 symmetry in the Euclidean part. So if you have that symmetry, then generically you have a crunch solution inside. This you demonstrate by looking at this coupled system of equations. Then you go to the boundary, and you have some type of theory on the boundary. And this theory on the boundary to study is easier than to study black holes, because you find out that the singularity reaches the boundary, or if you wish, the UV degrees of freedom of the field theory in a finite time. So there is a representation of the problem on the field theory side. And you try to see what is a representation. And the lessons are the following. You can have a theory on the boundary which has a relevant operator. If the relevant operator has a positive sign, so let's think of a mass squared, let's say that you have m squared phi squared, this theory now, when you go back into the bulk, will have a singularity in it, but the singularity will not be a crunch, but would be that, as you know, what is the IR limit of a theory which has a mass? You go just to the vacuum state. If you have some interesting topology, okay, you will get more than just a vacuum state. But generically, you just end up with a vacuum state, which means that in the bulk, you have drained out a piece of the geometry, and you create what is called a bubble of nothing. So this is the situation when you add a positive relevant operator. When you add a negative relevant operator, you may succeed that in this new vacuum, you still have many degrees of freedom. If you have there many degrees of freedom, you have a non-trivial geometry also here. And it is this geometry which in the bulk has a singularity. I'm not showing here again the details, I'm telling you just the fact. So you have here on de Sitter space, but no gravity, just an expanding universe, you find yourself in a situation where you have a well-defined theory. So the boundary theory tells you there is no problem. Everything goes well. The bulk has in it a singularity. How do you see on the boundary that there is a problem? You change coordinates, and I think I gave a talk about this several years ago here, and you can expose that singularity. But if you use this conformal boundary, this is a bread and butter spontaneous ON, let's call it, or some other spontaneous global symmetry theory. And it looks perfectly well on the boundary. It has a singularity in the bulk. So that means that you can try and reconstruct details of what happens in the bulk. And we took a quantum mechanical example in a paper. And I think the thing to remember about that, you would imagine that the term R phi squared, which appears every time you have the conformal field theory, and then you perturb it, but you have the term R phi squared, you would imagine that in quantum mechanics it disappears. But actually, to our surprise, we didn't see it noticed before, it does not, because the curvature goes to 0 at the same rate as the conformal coupling, which multiplies it, goes to infinity, and the product is finite. Usually, in 4 dimensions, you are used to have a 1/6 multiplying the R phi squared. But there is a general dimension structure of that, and when d goes to 1, that is quantum mechanics, the coupling explodes, the curvature goes to 0, and the product is finite. So you can play with this and see how you do diagnostics of a theory which on the boundary has no problems, which means it doesn't have problems, while in the bulk it does. And okay, then I would say in one word, you can also have a theory where the theory has an operator, for example, marginal or relevant, which is unstable. If it's unstable, also the bulk is not curable. So you will have a problem on the boundary, and you will have a problem on the bulk. There is an interesting number theory problem which arises if you allow this thing to oscillate. A butterfly effect, like the Kapitsa problem of the inverted pendulum, and actually that has very interesting structure in number theory. I won't discuss it. What is the point which I wanted to discuss for further reference? The point for further reference, okay, here I just told you the facts. For further reference, the point I wanted to discuss is this. Okay, I told you about T-duality. You all know about the story that if you have a circle, it's R or 1 over R. Now tell me, how do our brains know? Because after all, the universe could be in one direction at a circle. We have no evidence that it's not. We don't have any evidence that it is. So let me announce now that the discovery was just made in some new experiment that you never heard about, and they just discovered that there is a circle. So how do we decide if it's R or 1 over R? How do we know to say that? Okay, in my opinion, the reason is the way we are built by looking at local observables. This is our structure. So for us, the momentum modes and not the winding modes are the natural probes of the system. So our distinction of R and 1 over R goes by momentum modes. We think through localized wave packets or local plane or plane waves. Winding modes are not built into us. Now, our feeling is that the same thing happens when you have the two dual descriptions of this singularity in the bulk. That is, if you have probes which are local, then you will not know, let me do here, again, I will jump on all this, I will just use this. If you have probes which are local, and you live in De Sitter, you will not know that there is a crunch. You can go on your hammock forever. If you build probes which are very large and increase in size together as the Hubble constant grows, and your world volume, even though it's not gravitationally coupled, but it just grows, if you use such large observables, we believe that you would have doomsday people saying that they would know about the end. So this would be the analogy, and to me it's an open problem to identify these observables. What are the winding-like modes which would tell us that indeed a catastrophe is going to happen? In the coordinate systems in which you see a catastrophe, the oysters which would not see it would be objects which would shrink much faster than the Hubble constant on the scale. So they would never notice, because they are shrinking, they would not notice the imminent catastrophe. So to me, that's an important question to understand. Is it true that indeed the boundary theory says that the singularity can be cured without anything extra happening, as it would seem, or not? And I think this is one of the keys to look at it. Okay, now in the last 5 minutes, I will of that part, I discuss the issue of complexity. I defined complexity last time. I'm glad in private to give people again, tell them what complexity is. And it was supposed to be a measure if it's, what happens, what is the structure of the singularity. And there was a conjecture which was born by looking at black holes for long times, that if complexity increases, then everything is okay. No singularities are formed in the process. However, if complexity decreases, then for a black hole, you would expect the horizon to be like a firewall. And this is what I told you last time. So we asked ourselves, what happens for various types of singularities? And what we found, the general structure, again, please close your eyes if you don't want to get a... What we found that in the cases we studied of singularities, and we had 3 types of singularities, that the complexity decreases towards the singularity. Of course, all the calculations cannot continue when you're string scale, because then your tools are not there. But till you reach scales which are string scales and curvatures which are of the order of string scales, appropriate 1 over, then you find that the complexity decreases. And one case is, for example, the Kasner universe. In that case, that's the most trivial example, because you just take the world volume and shrink it at t equals 0. So here, when I say decrease, increase, it's toward t equals 0. So you have to go back from positive t to t equals 0. This is the metric of the problem. This is a metric on the boundary. You can extend it because it's Ricci flat to the bulk. This is one extension which has the same boundary. You do the analysis of calculating the complexity. I told you last time you use the idea that you have an extremal volume surface. Never mind how. The final result of this thing is that as you approach t equals 0, the complexity decreases. And this is the volume of the CFT times the number of degrees of freedom times the cutoff you put, because you don't want to reach the singularity itself. So you're approaching it, but you're doing the calculations before the singularity. And this reminded us of, when trying to think about it, reminded us of the structures in models which Tibor used to play with. And those are the structures of which we don't know, again, these works of Berezinski, Lifshitz, and who did I forget? Khalatnikov, I forgot, and Khalatnikov. These works, we never knew if they are generic or not. But they had the property that the system, as you went towards the singularity, developed much larger time derivatives than spatial derivatives. So if you have a lattice picture, the system looked like in the strong coupling on the lattice. Each problem lives on its own, a quantum mechanics of the lattice. And this, as a state, is a very simple state. So its complexity is indeed very low. So somehow, the fact that we got it for Kastner may be less surprising, but we also got it for the cases I described before, which were the singularities sitting inside ADS. In all these cases, we found the singularities to decrease. The reason that the singularity decreases, if you wish, was the A theorem. Namely, in the computations themselves, and this will be the last thing. Again, please shut your eyes. Okay, and let me show the results of the calculation. So the results were that if you looked at the extremal volume, you found that the contributions you get from the part which is the UV part are of what I've written here. What you get from the IR part, these decrease with time, these increase with time. When you sum them up together, the reason that the sum decreases is because the number of degrees of freedom in the infrared is smaller than the number of degrees of freedom in the UV. And the process has in it a constant flow of degrees of freedom from the UV to the IR. So this is the final answer that you get, and it decreases. So with the prescription that the volume is what is supposed to be the complexity, we found for 4 types of singularities, they all had one common feature: the complexity decreased, which somehow gives you the picture of a system which is decoupled into many different space-time points. So maybe one step into getting a feeling of what singularities look like using the tools which actually are tools on the boundary field theory. And with this, I actually even fulfilled my promise, and I'm glad in private to discuss more, but this concludes this part of the singularity. I would maybe just say again, to me it was very surprising that we can live with a theory which in the bulk has a singularity. This is not what I would have expected. Usually we wait for the knight on the white horse to come and save us. Quantum mechanics, something, string theory. Here it seems that you can live without it. However, as I told you, there is the issue of what probes we use. And it could well be that with probes which we are not used, we have not yet developed in these theories, which are long extended probes, one would actually see the singularity even when you are on your hammock thinking you will never see the singularity. Okay, now I want to discuss anomalies. So when Tibor originally asked me to take essentially my Blaise Pascal lectures. So this was part of one of my Blaise Pascal lectures, and it was more to educate than for an advanced audience. So anomalies, kinkiness, whatever, plays a role in our physics understanding. And in string theory, as you know, there is the central charge minus 26 and the central charge minus 15, which come out of an anomaly, play a very important role in how we construct string theory. And the open question I want to discuss will be related to that. In gauge theories, it took many more decades to appreciate the fact that you can't write down any gauge theory you want. There are some restrictions on what you can do. And one of the restrictions goes under the name of gauge anomalies. And I would like to discuss simple examples of this and give an understanding of what happens, because physicists hate authority. So if somebody tells you, okay, you can't quantize the theory, they say, why not? I want to quantize it. So what punishment will you suffer in the situation where we'll ignore these anomalies? Now, in general, how do you get to anomalies? So you have a certain, our way, we are, maybe this will change. Not the show, here. Here, I think. So this here. Okay, we'll start here. So one set of very interesting lectures could have been, should we really continue and write Lagrangians and actions? This has been a very successful way of doing physics, but as you know, we are very ungrateful, and everything that succeeds, we afterwards say, maybe we should have done it differently, and ignore it. So one point of view, which is you have heard probably many times recently, is maybe one doesn't need Lagrangians. Or, not that you don't need them, but there are circumstances where even if you want them, they aren't there. You have no idea how to write them down. Now, the usual way, we write first the classical Lagrangian. We identify its symmetries. Okay, now we can be pleased by it having symmetry, or we may not care if it has symmetry. But it seems that in order to understand at least the basic interactions which we observe in nature, assuming a symmetry, which many call now redundant, which is gauge symmetry, was a very useful way to do computations and to confront them with experiment. So we have spent a lot of time in writing down Lagrangians of systems which are gauge invariant. And they contain spin 1 particles, and they contain spin 1/2 particles, and they contain spin 0 particles. Now, the symmetry played a very important role, especially when one tried to take into account the full quantum mechanical structure of the theory, that is, do renormalization. When one does renormalization, one finds out that what is called the quantum Lagrangian, which is a true one, cannot preserve the symmetries of the classical Lagrangian. Now, sometimes maybe it cannot preserve at all. Sometimes you may be in a situation where this Lagrangian has several symmetries. And by preserving one, you can do it, but you cannot preserve others. And then you are faced with a choice. Maybe I don't give a damn about all of them. Maybe I want to preserve one and not the other, and what will be the consequences of doing that? So I want to exemplify these in simple cases. I will start with a quantum mechanical case. Now, in quantum mechanical case, you can say you talked about renormalization, you talked about the infinities. How will you see any type of anomaly in quantum mechanics? So actually, when one discovered anomalies, gauge anomalies, they came in two parts. One wrote down some partition function. And the question was, this could be some regularized partition function. The original one had a symmetry, a full symmetry. And you ask, what happens to that when you apply to it a gauge transformation. So how is Z of A of G related to the original Z of A you had? Now, the gauge group, as a gauge group, is of course a local symmetry, but itself has a local structure and a global structure. And I will show here in the example in quantum mechanics, we will actually discuss the local gauge symmetry, but its global part. Global not in the sense of that it doesn't change with space-time coordinate, but it's part of the global structure of the group. Because the group of gauge transformation is some group. And this group has local structure, let's say near the identity, but it can also have some non-trivial topology. And you can ask, how does this object behave under large gauge transformations? And this is the anomaly I want to discuss. Now, the system I'm going to take will first have a quantized gauge, and then the gauge will not be, the gauge field first will be not quantized and then will be quantized. So it's a very, given the time, again, I'll take a very simple system. I'll make it abelian. You can discuss the same thing for non-abelian systems. And the reference for this is work done together with Shmuel Elitzur, Yitzhak Frischman, and Adam Schwimmer. Some of them say it's too trivial to be worthwhile even to mention. I will mention it. So the Lagrangian we are going to take will have a complex, will have a fermion. So it will be a fermion psi of t, and it will be coupled. So there is only time, because it's quantum mechanics, with the t component of A to psi of t. This will be the Lagrangian. Because I am in the appropriate number of dimensions, I don't need to worry about gamma 5 or gamma 0 and so on. Just they are all defined to be ones. Now, this system is invariant under certain symmetries. It has a gauge symmetry and it has a global symmetry. And the gauge symmetry will construct so it has a global part and a local part. So what is the gauge symmetry? So there is a U1 local gauge symmetry. And that is if I take psi of t and I multiply it as one is used to by e to the lambda t, that would be, I take psi of t and multiply it by that phase. I take psi bar and I multiply it by this phase and shift A of t into A of t plus dt of lambda t. This Lagrangian, as written, is invariant under that symmetry. It is also invariant under a global symmetry. This is the symmetry I will present to clash with. And that symmetry is take and interchange psi and psi bar, and take A and move it into minus A. That is what you would expect from charge conjugation, so let's call it charge conjugation. This is a global symmetry. I do that symmetry at one point. I take psi to psi bar and A to minus A. Now, in order to give this interesting structure, because I want to build a case where there is an anomaly. So I have to give some structure. And the structure is I'm going to put T on some region from 0 to capital T, and I'm going to impose periodic boundary conditions on the gauge field here. So I have T goes to, the t goes from 0 to t, where from the point of view of the gauge field, I want to impose periodic boundary conditions. Okay, so now I won't show you, but it's a trivial exercise you can do for yourself. Just interchange psi and psi bar, put a to minus a, and then try to get back your original Lagrangian. Remember the anti-commutation relations of the psi's and psi bar, and remember the psi and psi bar, the anti-commutation relation is 1. You will retrieve back this model after doing this. So therefore, you know that you have two symmetries at the classical level. Okay. Now, just note for a moment that when you look at a system, you write down, which is also actually modern today, you write down all line integrals, all things that sit in that system. So for example, let us consider the Wilson loop. So I can write a loop, or in this language, some people sometimes call it the Polyakov loop, because it goes in the temporal direction. Let's look at this object from 0 to t, a of t dt. Now, let us check its gauge invariance properties. So if I substitute in here, I substitute this, I have the first term is the term, so now let's do the substitution. So I'm going to get the original term, which is exponent of I a dt from 0 to t. And I'm going to get a second term, sorry, it will be a product. And the second term, because I have a total derivative here, is going to be I times lambda at t minus lambda at 0. Now here you will see the structure of the gauge group coming into play. I could say that I wanted the gauge group be such that at the edges, both lambda of t and lambda of 0 should be 0. Namely, I'm interested only in local gauge transformations, which they start and they end at the same point, for example, the identity. I don't allow them to change. In that case, for those transformations and the class of all lambdas which obey this, this will be the local part of the local gauge invariance. The Wilson loop, which is the quantity here, is invariant under them. Another quantity, however, which would be in another set of gauge transformations, which would be invariant under them, would be the large gauge transformations. And I could allow myself that lambda of t minus lambda of 0 not be the same, but be 2 pi n. This would also keep the theory invariant. Now W and this action here is invariant under both. So I have the full gauge transformations here. Okay, and however, there is only one lesson to learn. Usually, and I will do it in the second example when we go to 2 dimensions, usually when you quantize a theory, or a nice way to quantize the theory is by going to the gauge A not equals 0. There you can have Gauss's law, and you have the Hamiltonian, and then you diagonalize your theory by submitting your wave functional to Gauss's law. And by this, you reduce the number of degrees of freedom from d to d minus 1 with A naught. And by applying Gauss's law, I will repeat it on the states, you get d minus 2 degrees of freedom. Okay, but in this system, is it possible to always go to the gauge A naught equals 0? The answer is not, because one of the things which defines the system is the value of the Wilson loop you have. Now, what is possible, you can take any configuration A of t and turn it into a time-independent time-independent field. So any field that I give you as a background, or afterwards I'll integrate over A of t, can always be reduced to a constant. And the value of the constant, this can always be taken by a legal gauge transformation, by a local one. It will be here 1 over t, if you wish, the average of A of t dt from 0 to t. Okay, another place where this average comes in, but for a different reason. And this object, dA bar dt, by definition, vanishes, because I've taken out all the t dependence in it. Now, how will A bar change under the residual gauge transformations I have, which are the gauge transformations which have this property? So I can take, for example, a local gauge transformation, which could start from 0, let's say, and end at 2 pi n. How would A of t change under this gauge transformation? So this, as you see, is part of the local part of the global. This is part of the global part of the local gauge transformation, because at time 0 and at time t, it has different values. Cannot be deformed to the identity. So under this, you will see that A bar goes to A bar plus 2 pi n over t. So unless you are in a situation where already this object here has been arranged to be a 2 pi n, you cannot take and go back to 0. So you are in a situation where you have a remnant of the gauge group, which you have to maintain as a symmetry, and has to remain a symmetry of your partition function. And that is the one where A bar gets shifted in such a way. The Wilson loop and this will have different values, depending on with what background I put. I cannot go to A bar equals 0 unless I'm in a very special configuration. Okay, so these are the constraints we have. And now we have to go ahead and calculate the partition function. Now, there are 2 ways to do it, and this is part of the question I'd like afterwards to ask you. There is one part which is very complicated on some scale, and that is, at least for someone learning quantum mechanics, would be complicated. And that just do the integral over psi and psi bar, and see how the thing depends on A, using the Lagrangian. I will show how to do that. But then the same thing can be done with the Hamiltonian. And the Hamiltonian gives it the answer in 2 lines. While the Lagrangian, as you will see, if one likes long calculations, it is a long calculation. So now let's do the functional integral over psi and psi bar. If these were bosonic degrees of freedom, we have a Gaussian, the Lagrangian is Gaussian in the field psi. We would have a determinant to the power -1/2, let's say, if it would be one real field. Because these are Grassmann variables, you get the opposite sign. So what you would have here, when you calculate the functional integral, you would get that z of A bar, remember, I used gauge freedom as much as I could. I fixed this down to the integer part, the appropriate, I kept the opposite. I kept the fractional part of the value of the background field, which I cannot modify anymore by gauge transformations. It's gauge invariant. And I look how the partition functions depends on that. And this was the result by integrating d psi, d psi bar, and we had an exponent of I s over h bar, and we just went ahead and did it. So this result is the determinant of the linear derivative minus dt plus I a bar. Okay, and if you wanted some infinity in quantum mechanics, you got it here, because this object here needs regularization. It's an infinite product, this determinant, so you need to regularize it. So the question comes now, how to regularize it. And now we keep in mind that there were two symmetries which at this stage we treat the same. We don't prefer one to the other. We would like to maintain that Z A bar gauged under the global part of the local gauge be equal to the original Z of A. That is under the 2 pi n over t. I want the symmetry. And I also want that my regular partition function be Z of minus A. And the question is, can I keep these two things together? This was a global symmetry. This is the global part of a local symmetry. A global, again, from the point of view of the topology, not in the sense that it's a global transformation. And can we do it? Okay, that's a question. You will see in the Hamiltonian calculation, it's very easy. Immediately you see what is possible and what is not possible. Here, you need to work. So there is one way in which one does the calculation in higher dimensions, and that's called Pauli-Villars. What you do is you take the system at hand, you add to the system at hand a mass term. The mass term, by definition, obeys no matter global, local part of the symmetry of the gauge group. It's always there. And if you look at this object, you have changed the theory. But then what you do is, you take the mass to infinity. And when you take the mass to infinity, you can do that, which means physically you have decoupled that particle. Now, we will see in the short part of the second part of the second part, is that you can't always decouple massive particles. When there is an anomaly present, the revenge will come at you. But here there is no anomaly because I took care that all the symmetries, the gauge symmetries, be preserved. So I can just take M to infinity, and I can see what happens. So now, in order to be able to do that, one actually needs to add a few Pauli-Villars. I will write to you how this goes on. And see if there is some combination which will give you a finite result. Whatever that finite regularized result is, you're sure it's going to be invariant under all types of gauge transformations. And you are at its mercy if it's also invariant under A goes to minus A. In this way, you do it, you don't prove that there is no other regularization which would preserve both. But on the other hand, you respect the old tradition of using Pauli-Villars, which is an indicator that that's the case. As I told you, when we go to the Hamiltonian formulation, you will see immediately what is possible and what is not. You won't have to go through the phase space of all possible regularizations. Okay, so what do you have in the case here? So the partition function Z of alpha, which is regularized using Pauli-Villars. You actually have here two masses you need in order to get the finite result. So you take both to infinity, and what you have here is determinant of minus t plus I alpha bar multiplied by the determinant of minus dt plus I alpha bar plus m1, which will be taken to infinity, to the power alpha 1. And if this tells you, if you wish, alpha 1 here tells you how many species of Pauli-Villars particles you want to take. But this is a mathematical regularization, so it doesn't have to be an integer. But in principle, it would tell you the number of species, because the determinant would go up by the number of species. Then you would have here determinant of minus dt plus I a bar plus m2, all this to the power alpha 2. Now,
Why do you have m1 and not I m1? No, if I add m psi bar psi, this adds to a, not to I.
If I add, no, I need, the truth is I don't remember now, but as far as I remember, this is a correct thing, and I will have to justify to you how to do that, why to do that. This turns out to be finite when 1 plus alpha 1 plus alpha 2 vanishes, and when alpha m1 plus alpha 2 m2 is 0. So you see that if I have here an I in the conditions, it would fall. So now one can show it in detail. And what you get here is, this is for you now, just so one sees. So there is a limit of m1 goes to infinity. The limit of m2 goes to infinity. And then you have a product for n going from minus n1 to plus n2, where n1 go to infinity and n2 go to infinity. I mean, nobody tried to play here double scalings. I don't know if there are several ways you would do it. At this stage, it looks like it doesn't matter how they play. Maybe there would be a little more structure if one would relate the various ways of going to infinity. In any case, you get this product of, so you have a free field, so you know you have 2 pi. These are fermions, so when you do functional integrals, we have something going from 0 to t. So for the gauge field, I emphasized it's periodic. But if you want to preserve the quantization for the fermions, you have to do anti-periodic. So that's why you have here the n plus a half plus a bar. This comes from the first thing. And then you have this multiplied by 2 pi over t n plus a half plus a bar. And here is what you asked. So maybe I just omitted the I there. And here, and then here, okay, the I, remember it's I dt, which is the, so, again, this, we have to go through, I don't remember. So you take this product, and this now becomes products of gamma functions. So if you define now
we can see the blackboard.
okay? So now this becomes Z Pauli-Villars of A bar becomes to be the limit of Mi goes to infinity, limits of Ni goes to infinity, where Mi was defined to be Mi t over 2 pi, and A, which will come in a moment, is A bar t over 2 pi. and you get this limit, and you have here the gamma function of n2 plus 3/2 plus a divided by the gamma function of minus n1 plus 1/2 plus a, and then you have here ratios of n2 plus 3/2 plus a plus I m1 and then you have something similar to the power gamma 2. Should be n2 plus 3/2 plus a plus I n2. This to the power gamma 2, and here you will have the gamma of minus n1 plus 1/2 plus a plus I n2. Okay. Okay, as I said, nothing is known here about the double scaling limit, if they are needed or not. In any case, this now goes down and becomes the limit of mi goes to infinity of cosine pi a times and you have here cosine of a plus I m2 to the power alpha 2. And from here, you get the conditions which I've written up there. And the final, once you take them into account, what do you get? You get 1 plus exponent of I a bar t. What a long way to get such a simple result. But that's the way. And yes, please.
It was a typo on the board upstairs. In the infinite product, there is alpha 1 and alpha 2 powers which are omitted.
Yes.
Yes, it was just.
Yes, here. You mean here?
Yeah, it should be to the power alpha 1.
Yeah, yeah. Okay, you correct it. Okay, yeah. At least here they were not. So this is the answer that one gets. This answer has two properties. It is invariant under the transformations that remained from A bar. So I remind you, what did A bar need to do? A bar, we were checking, is this invariant under A bar goes to A bar plus 2 pi n over t? It is invariant under that. However, it is not invariant in general for A goes to minus A. So we saw that Pauli-Villar's regularization gives you a regularization which is gauge invariant, but doesn't work for A equal A bar. You're not invariant under A goes to minus A bar. Okay.
By the way, if one had used the usual 1/2 I d by dt both ways, this is to say the antisymmetry between psi bar psi dot and psi bar dot psi.
No, would not.
Would not
You will see where the you will see where the ordering and tricks of ordering come in, but not at the Lagrangian level.
Because the Lagrangian is not real Hermitian.
Yeah.
Like if I Hermitianize it explicitly, maybe I get a real.
No, I think this is a standard Dirac Lagrangian. It's I d slash.
Yeah, but it's modulo surface term. Anyway. There is a better, which is Hermitian. Okay. Which I think is a real.
Part. Okay, we can discuss playing that game. But
Which would be cosine, which would be then symmetry.
well, this one, I chose that one. It has the symmetries I wanted, so I can do that. And then we can see what happens if we want to change it. So one thing is, you can ask, how do I make this invariant under a goes to minus a? Okay, that's a legitimate question.
I think that's what Thibault said.
Yeah.
You multiply by the face and you get cosine.
No, actually, to do that, I need to multiply by a term which is not gauge invariant. I need to add to it a term which is, if I would multiply that by an exponent of minus I a bar t, this, a bar capital T over 2, this would do the job. But this term is not gauge invariant in general under the transformations we have discussed before. It will depend of if n is even or odd. So I can do this, okay? I can try, and this is actually looks like a Chern-Simons term, if you wish. I add, because in this model, this is the Chern-Simons-like term. I add this term. I can correct and now have ZA equals Z minus A, but I have lost, for a general value of n, I have lost the symmetry. So in that case, I have, okay, that again, it doesn't say that this is the only way to do it. Maybe there are other ways. But this particular way left us with one symmetry and not with the other. You can play around, but I think this is the easiest way to see it, that in order to be able to make it invariant, that is, turn it into a cosine, you had to multiply it by a function which itself is not in general invariant under the global part of the local gauge transformations, not the most general ones. There are some for which it is, let's say half for which it is, and half for which it's not. So this is the result that one obtained. If one starts, again, given the time, I won't now show you that, but you can start in a way which ab initio is natural. You are guaranteed at each step that you are going to have charge conjugation. You don't care about gauge invariance, but you do a charge conjugation regularization. It's a little different. And then you indeed get the result that you would get by multiplying these. So you would get that you are, as you are guaranteed at every step, you will also in the limit we charge in conjugation invariant, but you are not invariant under the general where was it? Not under this general transformation because of this factor 2 which enters in. Okay, so this was an example of how two ways, one which guarantees gauge invariance, which is the Pauli-Villars, which now the file comes back to me. I think the I is what is special about Pauli-Villars. So actually, you put it there. They are not natural fermions because you put the I. That was that was a trick of Pauli and Villars. And I'm sorry, the file dropped after a while. And on the other hand, if you do, I didn't show you, the natural regularization, which obeys charge conjugation, you're going to find out that you obey charge conjugation, guaranteed, but you will miss gauge invariance. Okay, so the first question, it's always terrible, Solomon's choice, whom to choose to sacrifice. And maybe sacrifice both. I mean, who cares about them actually? Or do I choose one or not the other? This decision cannot be made immediately. It has to be made once A is quantized. If A is not quantized, it's left to the arbitrary will of you. You can keep one, you can keep the other. There are other ways to regularize it, and then you will have neither. Now, let me show you, before we make the Solomon's decision, which in this case is, again, you choose one and not the other, is how would this look in the Hamiltonian formulation? Now again, I should emphasize that this type of anomaly for decades was missed and actually was discovered by Witten in the mid-80s maybe or something, because for decades nobody realized that this extra imposition is, and it actually gives you a limit on the number of, on the oddness or evenness of neutrinos, for example, that you are allowed to have in your system. So it has consequences. It's here just a quantum mechanical example, but it has more serious consequences. Okay, here, Thibault, I will do what you want. I will take ambiguity in ordering into account. So we know what the classical Hamiltonian is. It's a system which is first-time derivative. So you know that when you do the Legendre transform, you will actually not see the conjugate momentum because it's a first-time derivative, so it drops. And all you're going to see is back the term you had itself. So the Hamiltonian of the system is going to be I, A bar. Okay, but how, in what order? So now that I'm going to quantum mechanics, I know that I can have this, I can write it like this, which is a little bit what you want it to do, and write it like that you can.
I don't want the I.
Okay, but
Hamiltonian is Hermitian.
well, it depends, as you know, on how we decide how we do that. So let's not quarrel about that now, even though I agree that out of all numbers, 2 pi's are less important, i's are crucial. This I would agree. So under the condition that alpha minus beta equals 1, I can have any type of combination. They're all legal. They all have the same classical limit. So the problem here, which was the problem of regularization, I had a determinant. It's an infinite product. I have to define it. Transmutes into a much simpler problem. I just have the issue of ordering. There's nothing else. There's nothing infinite here. But I do have the ambiguity in how I want to order this. And the results will depend on how I order this, because it multiplies, this will multiply the A bar. And we saw that the gauge dependence will depend on that. So to look at such a Hamiltonian in the general case, yeah. Okay, even in the regularization, you can already see that in order to have one charge conjugation symmetry, for example, that would require that beta equals -1/2. In order to have the symmetry that you change psi and psi, psi dagger and psi, and A with -A. Now, in general, you can now go ahead and calculate the partition function. And the partition function, this operator, psi, dagger psi, the number operator has 2 eigenvalues, 0 or 1. So when writing down the partition function, either the fermion state, either you have a fermion or you don't. And this, you just sum over these 2 options. And when you do that, that's a very simple thing. You're going to get the exponent of, if I removed alpha and remain with beta, I'm going to get here exponent of -A bar t times beta times 1, which I get when the state is empty. And then I have, when the state is full, I would have an exponent of -A bar t. So this is my partition function. So here, only ambiguity I had was the ordering. And I have to see, is there a value of beta for which both symmetries can be preserved? I showed you or told you that when you do this transformations, you will get beta equal -1/2, which tells you already that it's not going to be the case that you can keep both. So here, unlike the Lagrangian, where I really had to prove to you that there is no regularization which exists, which can preserve both, here you see, depends what beta you are going to take. You can arrange to get both, both violated, or you can have one of them. For example, if you took beta equals 0, you would have one of them. If you took beta equal n, you could have the gauge transformation. If you take beta equal minus a half, you got charge conjugation, but you did not get the other symmetry. Okay, so this shows you an example where the Hamiltonian is so much simpler than the Lagrangian. And I wonder, I don't remember, I think Landau suggested to bury the Lagrangian with the honors it deserved, or one of them was suggested to be buried with the honors it deserves. I think it's the Lagrangian, but it could be the Hamiltonian. In any case, you see that in this particular example, it's really much easier to look at the Hamiltonian formulation. And I'm wondering if there are other systems where you have very complicated calculations doing a Lagrangian, if things could simplify when you look at the subsector just through the Hamiltonian. Okay, now let's make, so here we saw that for gauge invariance, beta should be n. We had a case where n equals 0, but other integer n's would work as well. And the minus a half doesn't work. Now, what about the quantum mechanics? So in the quantum mechanical case, the way this manifests itself is, what is Gauss's law? Now, Gauss's law on the states is obtained by the derivative with respect to the variable which is not cyclic, or sorry, which is cyclic, which is A naught or A bar here. So Gauss's law would tell you that when acting on the state, let me call it the operator G, which is psi dagger psi plus beta. So when G acts on a state psi, minus beta, I should get 0. That's a claim. That's Gauss's law. Now, in general, we started with the example of beta equal 0, and that was okay. But if I take beta equal minus a half, there is no way I can add fermions and obey this condition. If I take beta equal n, it means my system wouldn't have one fermion, but I would have n, and it could work. But for beta equal minus a half, there is nothing I can do, which means my Hilbert space is empty. And this is a manifestation in a Hamiltonian formulation. This is true in higher dimensions. The way that Gauss's law comes, the way you see that in the quantum theory, you cannot give up the symmetry of global transformations is that you will end with an empty Hilbert space. In the Lagrangian formulation, you would integrate what I've written, which was with beta equals 0. This was a partition function. If you integrate it over dA, a bar, which you should, if it's a functional integral, it would vanish to 0. So there are two ways to see it. In a Lagrangian formulation, where you have a global anomaly, you integrate over the gauge field. When it's quantum, you get 0. So the theory, you don't have a partition function, you can't define anything. It's cleaner to me in the Hamiltonian, my Hilbert space is empty. So I put too much, the system is over-constrained, too bad. So I will have to sacrifice, with great regret, charge conjugation. So the system, even though classically it looked like it had charge conjugation, the consistent quantum theory cannot have charge conjugation. This is the example for the global anomaly. Now, can I give an example of the local anomaly? And this I will do in the 5 minutes which remains. I will, because I can tell you the consequences. So this I cannot do in quantum. We don't know how to do in quantum mechanics, but in a work which I did again with Adam Schwimmer, Ian Halliday, and Mike Chanowitz, we tried to take a model which can be solved exactly, even though it has an anomaly. And that is the Schwinger model in 2 dimensions. Just go ahead and solve it and see what it gives. Now, the open problem I have in mind, which I think has not yet been solved, and I wish I would have solved it, but if not, someone else solve it, is do non-critical string theory, but don't do the trick of making it critical by adding the appropriate coupling. Leave it non-critical as it is, and quantize it and solve it and see what theory this gives. Because all the way up to now where people did what they call non-critical string theories by actually canceling the anomaly by adding a piece to the system and then solving it, which is interesting, gives very nice results, but it doesn't face the problem of what happens if you disregard the rules, the authority, and you just do it. And bad things should happen. So let's see how in general one would look, and then look at the 2-dimensional case. So what is the general structure that you would expect? So just like you can do with the Wheeler-DeWitt equation, you can do, or was done much earlier, counting degrees of freedom in the cage of gauge series. So you know you have a gauge object, A mu, which has d degrees of freedom. You can go and forget now the global structure issues, which I discussed, to a gauge where A not equals 0. So the problem became d minus 1. You write down a Hamiltonian, but you find that the generator of gauge transformations which keep A not equals 0, which means the time-independent gauge transformations, that generator is just Gauss's law. And let's say the Hamiltonian is E squared plus B squared. G for the free case would just be del dot E. In general, would also have minus some charge density. E and B don't commute, because E and A are conjugate variables, and B is curl of A. But nevertheless, when you do the calculation, because this is the generator of the residual gauge transformations of the system, this will vanish. You do the calculation, and you find that H and G vanish, which means that you have the super selection rule, a freedom to diagonalize the two simultaneously. And the way you get the correct number of degrees of freedom, you say, OK, I diagonalize H, and I look at all eigenfunctions of H. However, I pick only those eigenvalues, only those eigenfunctions which are annihilated, let me call it Gauss's law is better, by Gauss's law. This will be the sector where, for example, Lorentz invariance will be resuscitated, because here I made an explicit breaking of Lorentz invariance. But because the theory is gauge invariant, then if I work at the subset of states which are annihilated by G, I look at the spectrum. It is a dispersion, a relativistic dispersion relation. I have resuscitated it, and the number of degrees of freedom went to what it should be, d minus 2. And you can do the same with the Wheeler-DeWitt equation and go from, in the gravity case, from the number of degrees of freedom embodied in G mu nu, which is d times d plus 1 over 2, reduce it by the same type of operations, go to the synchronous gauge, impose fourth or d type of Gauss's laws, and you will get the same counting. So this works very nice. Is there any loophole in the argument I gave? Yes, there is one loophole. I have assumed that I can simultaneously diagonalize all the G's, which means I've assumed the G of X and G of Y vanish for every X and Y. If they don't, then I stop there, because I cannot diagonalize them at the same time. And the point of anomalies which appear, not the topological ones I've discussed, but the simpler ones which were known for many decades, the ones which are related to gauge transformations which are near the identity is that this doesn't vanish. When you have series where this doesn't vanish, you have an anomaly. Now, where does it come from? It doesn't come from the part del dot E. It comes from the part rho. Now, it's true that in non-abelian gauge series, like in the Wheeler-DeWitt equation, you don't get that the constraints commute, but you get on this side another constraint. So on the subspace where the constraints vanish, it does commute, and therefore it works well. So if you have a pure gauge theory, let's say just QCD without quarks, there is no problem. There are indeed, there is a I and there is a J, and there will be here a GK, and there will be some FIJKs, or whatever appropriate structure constants, but on the subspace where the G vanishes, they commute, so there's no problem. However, the rho part, this is where the chiral matter comes in, doesn't have that property. There you have derivatives depending on what dimensions you are, but you have delta functions or derivatives of delta functions depending, again, how many derivatives appear depend on your dimensionality. And in particular, in 2 dimensions where you can solve the problem, when you add chiral matter means that ER is different than E left. You're going to get here some, let's say, something which is ER squared minus EL squared multiplied by a derivative of a delta function. So that will be a situation where you have an anomaly. So in general, a lesson to take away independent of the details of the model. The way that the anomaly manifests in a Hamiltonian formulation, if it is the local part of the local group, gauge group, it's the fact that Gauss's laws don't commute. There is a C number, of course, not commute, there is a C number on the right-hand side. On the other hand, when you have a global part of the local gauge group with an anomaly, the Hilbert space is empty. You have over-constrained your system. You will find no state which obeys the laws. So you have to have a theory where this anomaly is cancelled. And you cancel it in string theory when we have the conformal anomaly. We speak very roughly. We speak about 26 dimensions. We speak about 10 dimensions. We can speak about other ways of doing that. That's the way we cancel the anomaly in string theory. The way you cancel the anomaly in SU5 is by having a 5 bar and a 10. The way you cancel it with gravitational anomalies is by having relations between leptons and quarks. There are many and crucial ways in model building where the anomalies come in. So to conclude, because this would have been lecture number 5, which will not happen. So if I would solve this model exactly, it can be done in 2 dimensions. I would solve it in the gauge A not equals 0. So the first thing is, should I expect a Lorentz invariant dispersion relation? I see no reason. If the theory has an anomaly, if E left is different than ER, there is no reason why the gauge A not equals 0 would be Lorentz invariant. I picked a direction. And the answer is not Lorentz invariant. You get an explicit dispersion relation. You have in it E related to k to the force n to k squared. So it's not a relativistic dispersion relation, but you can solve the theory exactly. Then just like here you had, both of you suggested to multiply by this, there is a way here to add a Wess-Zumino term to cancel the anomaly. But adding this Wess-Zumino term is always equivalent to having ab initio another set of fermions which cancel the anomalies and integrating them out. And the integrating out gives the Wess-Zumino term. There is an ambiguity, and here I'm talking really to the super experts, there is an ambiguity on gauge invariant terms. The Wess-Zumino term canceling the anomaly is unique. But in the integral, they can also be gauge invariant terms. What do they represent? There are infinite number of ways to cancel an anomaly. If E right is different than E left, I can have an infinite number of distribution of charges which I add to my theory, each of which will end up exactly canceling the anomaly. Okay, for example, let's say that ER minus E left was 1. Okay, so I need to add an E left, which is 1. But I can add E left, which is 3. And then I can add an E right, which is 2. Or I can add 2 E rights, which are 1. There are an infinite number of ways to cancel the anomaly by adding extra stuff which is not anomalous. Okay, you just pick up the single part, which is, and that's what the gauge invariant terms reflect, and it's an interesting thing to know. And then the final surprise I had on the subject is there are in conformal field theories what are known as coset models. Coset models are models which are very interesting because in string theory they can replace geometry by algebra. And you can do exact calculations using the algebra instead of living with a semi-classical picture, which is geometry. So they have had, and I think will have, and are having lots of uses. Now, if you take a model which has a Wess-Zumino-Witten model G, it has a subgroup H, and you write the Sugawara construction as a different of the G's and the H's, this model itself is not a WZW model, but still is conformal, and its conformal charge is the difference of these two. And we have shown in the past with Korkut-Bardacci that this model can be written as a gauged, as a strong coupling limit of a gauged Wess-Zumino-Witten model. And you can see exactly how this model constructs. Now, the funny part is that if we have a group G over H, for cosets, so that's a strong coupling limit, that's a deep infrared of the problem. We found that actually you can gauge, I thought for years that I cannot gauge an anomalous symmetry. In these cases, you can gauge the anomalous symmetry, and actually you find a relativistic dispersion relation, which was to me a surprise. So again, these models you take by writing down some CFT, gauging that CFT, but not adding a term f squared. The term f squared in 2 dimensions has conformal weight. So if conformal invariance is not spontaneously broken, it will not be created, and indeed it's not created. But you could think also of the model with the f squared, and then just take the coupling, which is dimensionful like the mass, to infinity. It's the same consequence. And in that case, as I told you, somehow this anomalous Schwinger model remains with a relativistic spectrum, which to me is a little bit of a puzzle how that could have happened. So I think by giving puzzles which are concrete, and in the beginning telling you about an area which I find really very interesting and I believe will develop well, there will be interesting results, but in which things are not as well defined as we would like, and one needs much better definitions, which is a quantum information theory related to gauge theories and to gravity. I hope I gave you some feel of that, and I hope by this I finished my duties here on that, and the next Louis Michel professor will have to do the same now. Okay.